In the constellation Boötes, there is a space so huge that it could fit 1,000 Milky Way galaxies and still have room to spare. This is a place where galaxies almost completely disappear. Scientists call it the Boötes Void, and finding it surprised everyone, changing how we understand the universe. In this journey, we will explore this enormous emptiness, meet the few lonely galaxies that live inside it, and see how this vast void makes us rethink everything we thought we knew about reality. Cosmic voids, often referred to as dark space, are among the most mysterious and intriguing features of our universe. These enormous regions of nearly empty space stretch across unimaginable distances, lying between the largest structures in the cosmos known as galaxy filaments. Despite their vastness, cosmic voids contain very few galaxies or, in some cases, almost none at all. While the scale of these voids is staggering, most galaxies are not located inside them. Instead, the majority of galaxies are drawn together by gravity into enormous networks of galaxies called filaments, which make up the cosmic web. These filaments form the backbone of the universe's large-scale structure, with galaxies clustering along them, while the voids form the vast, sparsely populated regions that separate these dense structures. The formation and evolution of cosmic voids are fundamentally different from the development of the universe as a whole. In these regions, the curvature of space can dominate for long periods, which prevents the formation of galaxy clusters and the largest galaxies. Even though the emptiest regions of these voids still contain more than approximately 15% of the universe's average matter density, they appear almost entirely empty to an observer looking through a telescope. To put this into perspective, if you imagine the universe as a vast cosmic ocean, the voids would be the enormous stretches of open water between clusters of islands, with only the occasional tiny rock representing the few galaxies that manage to exist within them. Voids are truly immense in size. They typically have diameters ranging from 10 to 100 megaparsecs, which translates to approximately 30 to 300 million light-years across. To give a sense of scale, 1 light-year is the distance that light travels in a single year, about 9.5 trillion kilometers, so even the smallest voids are incomprehensibly vast. Some of the largest voids, which are defined by the absence of rich clusters of galaxies called superclusters, are referred to as supervoids. These supervoids can span hundreds of millions of light-years, making them some of the largest known structures, or rather, absences of structure, in the universe. The first discovery of cosmic voids came in 1978, when astronomers Stephen Gregory and Laird A. Thompson, working at the Kitt Peak National Observatory, published a pioneering study identifying these enormous empty regions between clusters of galaxies. Their discovery fundamentally changed our understanding of the universe's structure, revealing that space is not filled uniformly with matter, but instead has a vast, foamy, web-like arrangement of galaxies and empty regions. The origin of cosmic voids can be traced back to the earliest moments of the universe, shortly after the Big Bang, roughly 13.8 billion years ago. These voids are believed to have formed due to baryon acoustic oscillations, which are ripples in the density of the primordial matter created during the first few 100,000 years after the Big Bang. Essentially, regions of slightly higher density collapsed under their own gravity, compressing the matter within them, while lower density regions expanded to create vast empty spaces. The initial unevenness in the distribution of matter, which began as tiny quantum fluctuations in the very early universe, grew over time. Areas with higher density pulled in more matter, forming clusters of galaxies and filaments, while lower density regions expanded faster, eventually giving rise to the enormous voids we observe today. The resulting cosmic landscape resembles a vast three-dimensional foam or web, with filaments and clusters forming the walls and the voids occupying the spaces in between. Interestingly, voids located in areas of higher matter density are generally smaller than those in low-density regions, reflecting the influence of surrounding matter on their growth and shape. Cosmic voids are not only remarkable for their emptiness, but also for their connection to the cosmic microwave background, or CMB, the faint glow left over from the early universe. The temperature of the CMB is slightly different in various regions, and these differences correlate with the location of voids and filaments through what is known as the Sachs-Wolf effect. Colder regions of the CMB tend to coincide with voids, while hotter regions align with the denser filaments. This phenomenon occurs because of gravitational redshifting, where the energy of photons from the CMB is altered by the gravitational effects of surrounding matter. The Sachs-Wolf effect is only significant when the universe is dominated by either radiation or dark energy, which means that the study of cosmic voids provides valuable physical evidence for the existence of dark energy, the mysterious force that drives the accelerated expansion of the universe. To understand the large-scale structure of the universe, scientists often describe it using several key components that form the cosmic web. First are the voids themselves, which are vast, roughly spherical regions with very low densities compared to the cosmic mean. Some voids can reach diameters of up to 100 megaparsecs, or around 300 million light-years, making them enormous in comparison to galaxy clusters and superclusters. Next are the walls, which are regions of space that contain average densities of matter. Walls can be further broken down into smaller structures. Clusters are areas where walls meet and intersect, forming zones of extremely high galaxy concentration. Filaments, on the other hand, are the branching arms of walls that extend for tens of megaparsecs, acting as bridges between clusters and weaving the entire cosmic web together. While voids have mean densities less than a tenth of the average density of the universe, the precise definition of a void is still somewhat flexible among astronomers. Typically, the density of matter in a region is described based on the number of galaxies per unit volume, rather than the total mass of all matter present, which allows scientists to identify and classify voids with relative consistency. The study of cosmic voids began in earnest during the mid-1970s. Before this time, astronomers were limited to two-dimensional maps of galaxies, which often appeared densely packed and overlapping, offering little insight into the true three-dimensional arrangement of matter in the universe. The introduction of redshift surveys revolutionized this field. By measuring the redshifts of galaxies, shifts in their light due to the expansion of the universe, as described by Hubble's law, astronomers could determine their distances and map the universe in 3 dimensions. This approach enabled the discovery of not only superclusters, but also the large empty regions between them, now known as voids. In 1978, 2 separate teams of astrophysicists independently identified superclusters and voids, marking a major turning point in the study of the universe's large-scale structure. These discoveries demonstrated that the universe is far from uniform. Instead, it consists of an intricate foam-like network of dense clusters and vast empty spaces. A timeline of significant milestones in the study of cosmic voids illustrates how our understanding of these mysterious regions has evolved over the past several decades. In 1961, astronomers first brought attention to large-scale structural features in the universe, including what were called second-order clusters, a type of supercluster. These observations hinted at the presence of large-scale patterns, but did not yet identify the voids themselves. It was not until 1978 that the first 2 papers specifically discussing voids were published, describing empty regions in the foreground of the Coma and Athan 367 clusters. Just a few years later, in 1981, astronomers discovered a large void in the Boötes constellation, measuring nearly 50 megaparsecs in diameter. Subsequent recalculations later refined this measurement to about 34 megaparsecs. Around this time, advances in computer simulations allowed scientists to model the growth and evolution of the universe's large-scale structure more accurately, providing insights into the distribution of galaxies, filaments, and voids. By 1985, astronomers had completed detailed surveys of the Perseus-Pisces region, mapping the superclusters and voids in that area of the sky. These studies showed that the large-scale structure of the universe is dominated by voids, sharp filaments, and the walls that connect them. In 1989, the Center for Astrophysics Redshift Survey provided further confirmation, revealing that these structures are not isolated phenomena, but rather pervasive features of the cosmos. The early 1990s saw additional surveys, such as the Las Campanas Redshift Survey in 1991, which confirmed the abundance of voids throughout the universe. Comparisons of various galaxy surveys throughout the 1990s demonstrated that the same voids appeared consistently, regardless of the method used to select galaxies for observation, suggesting that voids are fundamental features of the cosmic web rather than observational artifacts. The early 21st century brought even more progress. In 2001, the completion of the 2-degree field galaxy redshift survey significantly increased the number of known voids, providing a more comprehensive view of their distribution. By 2009, the Sloan Digital Sky Survey, combined with previous large-scale surveys, offered the most detailed picture yet of the universe's cosmic voids. This wealth of data allowed astronomers to study the shapes, sizes, and properties of voids with unprecedented accuracy, improving our understanding of how these vast regions influence the evolution of galaxies and the expansion of the universe itself. The importance of cosmic voids extends beyond their sheer size and emptiness. These regions provide crucial insights into the nature of the universe, including the behavior of dark energy, the formation of galaxies, and the large-scale dynamics of matter. Because voids expand more rapidly than the denser filaments and clusters around them, they serve as natural laboratories for studying the interplay between gravity and cosmic expansion. Observations of how galaxies move within and near voids can reveal information about the distribution of dark matter, the unseen substance that constitutes the majority of the universe's mass. Additionally, voids help astrophysicists test theoretical models of cosmology by comparing predictions of void formation and growth with actual observations. Despite their relative emptiness, voids are not entirely devoid of matter. They contain small amounts of gas, dark matter, and occasionally a few isolated galaxies. These galaxies tend to be smaller, fainter, and less evolved than those found in denser regions, as the lack of surrounding matter limits their ability to grow and form new stars. Studying these isolated galaxies within voids provides a unique opportunity to understand how galaxies evolve in extreme environments and how the absence of nearby matter influences their development. Moreover, the distribution of voids and their properties can help refine our understanding of the early universe, particularly the processes that occurred during and shortly after the Big Bang. Cosmic voids also have intriguing effects on light passing through them. As light from distant galaxies or the cosmic microwave background travels through a void, it experiences changes in energy due to gravitational effects, leading to phenomena such as gravitational lensing and redshifting. These effects provide additional tools for astronomers to probe the distribution of matter in the universe, even in regions that appear almost empty. By carefully measuring the influence of voids on light, scientists can infer the presence of dark matter, map the large-scale structure of the universe, and test models of cosmic evolution. Another fascinating aspect of voids is their shape and distribution. While many voids are roughly spherical, some are elongated, irregular, or interconnected with other voids, forming complex networks within the cosmic web. The shapes of voids can reveal information about the surrounding cosmic environment, including the influence of nearby filaments, clusters, and superclusters. By analysing the geometry and alignment of voids, astrophysicists can gain insights into the forces that have shaped the universe over billions of years, from the initial quantum fluctuations to the large-scale patterns observed today. The study of cosmic voids is ongoing and continues to evolve with new technology and observations. Modern telescopes, both on the ground and in space, are capable of mapping galaxies with unprecedented precision, allowing astronomers to identify even smaller voids and study their properties in greater detail. Future surveys and missions will likely reveal more about the role of voids in the cosmic web, their influence on galaxy formation, and their connection to dark energy and dark matter. As our understanding of these vast empty regions deepens, cosmic voids are proving to be not just empty spaces but essential components of the universe, holding clues to its past, present, and future. When astronomers and cosmologists set out to study the universe on the larger scales, one of the most intriguing features they encounter are cosmic voids, vast stretches of space that are remarkably empty, almost entirely devoid of galaxies, stars, and conventional matter. These voids are not merely empty pockets of nothingness, but instead are essential elements in the intricate tapestry of the cosmos. They are as important as the filaments, clusters, and walls of galaxies that weave together the large-scale structure of the universe, often referred to as the cosmic web. Finding these voids is a challenging task because the universe is immensely vast and complex, filled with galaxies scattered across unimaginable distances, forming dense clusters in some areas while leaving immense stretches of emptiness in others. To systematically identify and categorize voids, scientists rely on the results of large-scale surveys of the universe, such as the Sloan Digital Sky Survey, and other detailed astronomical catalogues that map the locations and properties of millions of galaxies. These surveys provide an enormous amount of data, and to make sense of it, researchers have developed a variety of sophisticated algorithms, each designed to detect and classify voids based on different principles. Although these algorithms differ in technique, almost all of them fall into three main categories, each representing a fundamentally different approach to understanding the emptiness of space. The first category of void-finding algorithms is based on local galaxy density. In this approach, the central idea is that voids are regions of space where the number of galaxies is significantly lower than in surrounding areas. Essentially, these methods treat galaxies as indicators, or markers, of where matter exists and by contrast, where it is lacking. To determine the density in a particular region, astronomers often use a technique known as the nearest neighbour approximation. This method involves selecting a galaxy from a catalogue as a target, and then calculating the cosmic density in the surrounding area by measuring the distance to the third closest galaxy. By doing this for every galaxy in the catalogue, scientists can create a three-dimensional map of regions that are unusually empty. This method was introduced by Elad and Piran in 1997 as a way to efficiently standardize the cataloguing of cosmic voids. Once initial spherical regions or cells are identified from the data, each cell is gradually expanded until the density of matter reaches levels expected for the walls that define the boundaries of voids. One remarkable aspect of void regions identified in this way is that their edges are often very well defined, creating clear transitions from the emptiness inside the void to the denser surrounding regions. The central part of a void typically has a cosmic mean density of about 10% of the average density of the universe. This density rises rapidly to around 20% near the edges, and then it reaches 100% in the walls directly outside the void boundaries, where galaxy clusters and filaments dominate. After identifying these voids, researchers then analyze the surrounding regions, dividing them into distinct zones that include the dense walls, filamentary structures, clusters of galaxies, and the almost empty interiors of the voids themselves. If a new void overlaps by more than 10% with an already known void, it is classified as a sub-region of the existing void, rather than a completely separate entity. To maintain the accuracy of this method and avoid cataloguing regions that are empty simply because of random gaps in data, only voids with a minimum radius of 10 megaparsecs are included in the catalogue. This ensures that the voids identified are significant structures rather than artifacts of sampling errors or incomplete surveys. The second category of algorithms, while still focused on the distribution of galaxies, approaches the problem in a more geometric and structural way. Instead of measuring local densities, these methods examine the shapes and configurations of regions in the universe based on the distribution of galaxies and, by inference, the underlying dark matter. A key technique used in this class of algorithms is called Voronoi tessellation. Voronoi tessellation divides space into a network of cells around each galaxy in such a way that every point within a cell is closer to its central galaxy than to any other galaxy. This creates a patchwork of regions, each associated with a single galaxy, allowing researchers to identify areas where cells are unusually large, which correspond to underdense regions or voids. To refine the borders of these regions and reduce biases, astronomers also introduce mock border particles, which act as artificial markers to help define the edges more clearly. This method was notably introduced by Neyrink in 2008, and it was designed to operate without free parameters or assumptions about the shapes of voids. This was an important advancement because it allowed the algorithm to identify voids of more natural and varied shapes and sizes, rather than forcing them into predefined geometrical molds. Despite these advantages, the Voronoi-based method has received some criticism, particularly because it can sometimes produce loosely defined or trivial voids, small, inconsequential, empty regions that may not be meaningful in the context of cosmic structure. To address this, scientists apply a statistical significance measure to each void, evaluating the likelihood that it represents a real underdense region, rather than a random fluctuation. Additionally, a physical significance parameter can be set, ensuring that only regions with a minimum ratio of void density to average density, typically at least 1:5, are considered true voids. This technique also allows for the identification of subvoids, smaller voids contained within larger ones, which raises interesting philosophical questions about what qualifies as a void and how hierarchical structures in the cosmic web should be interpreted. One of the prominent void-finding tools that utilizes this Voronoi tessellation approach is called VID, which is based on the Zobov algorithm. VID has become widely used in the study of cosmic voids due to its ability to detect voids without imposing rigid shape assumptions, although the challenge of distinguishing trivial voids from significant structures remains an ongoing area of research. The third category of void-finding algorithms takes an entirely different approach, one that shifts the focus from simple underdensity to the dynamics of matter itself. In these methods, voids are not defined merely as empty spaces, but rather as regions where matter is actively moving away, driven by gravitational forces and the expansion of the universe. This dynamic perspective links directly to the properties of dark energy and the equation of state that describes it, often represented by the symbol W. In this framework, the centers of voids are identified as points where the displacement of matter is at a maximum, corresponding to the most extreme sources of what is called the displacement field, denoted secs. This approach allows scientists to calculate precise analytical properties of voids, including their shape, size, and evolution over time. Laveau and Wandel introduced this method in 2009, and it was designed to provide a more rigorous way of studying the geometry and dynamics of voids than the previous two approaches, which relied primarily on density or geometrical partitioning. One of the major benefits of this method, often implemented in a tool called DIVA, is that it can explore the ellipticity of voids, how stretched or flattened they are, and track how these voids evolve within the large-scale structure of the universe. By doing so, researchers can classify voids into three distinct morphological types. The first type, known as true voids, represents the most conventional understanding of voids, large, underdense regions with clear boundaries and minimal matter inside. The second type, pancake voids, are somewhat flattened or compressed in one dimension, resembling a thin sheet-like structure. The third type, filament voids, are elongated along the cosmic filaments, often appearing stretched between dense clusters of galaxies. This classification allows for a richer understanding of the diversity of cosmic voids and their roles in the structure of the universe. A significant strength of the DIVA approach is its ability to calibrate selection biases with high precision. While all void-finding methods are affected to some degree by biases in the data or limitations of the survey, DIVA's design allows for careful correction, making its results more reliable for certain types of analysis. However, this method also has its limitations. Because it defines voids in terms of the dynamics of matter, rather than purely density or geometric considerations, the resulting voids can be intrinsically different from those identified by the first two classes of algorithms. This discrepancy makes direct comparisons between datasets analysed with different methods challenging, as the definition of what constitutes a void is not uniform across approaches. Each of these three categories of void-finding methods has its own advantages and limitations, reflecting the complexity of the universe itself. The first method, based on local galaxy density, is relatively straightforward and provides a clear, quantifiable measure of emptiness, but it can sometimes miss smaller scale structures or overestimate the size of voids due to the simplicity of its approach. The second method, using Voronoi tessellation and geometric partitioning, allows for more accurate mapping of void shapes and sizes, capturing the irregularity of real voids, but it can produce many trivial or small voids that require additional filtering to identify meaningful structures. The third method, focusing on the dynamics of matter and gravitational displacement, provides deep insight into the evolution and morphology of voids, allowing for advanced analytical calculations and classifications, but its results are less directly comparable to those from other methods and depend on a more complex understanding of the underlying physics of the universe. Together, these approaches illustrate the richness of techniques available to cosmologists seeking to understand one of the universe's most mysterious and fascinating features. They also highlight the ongoing challenge in cosmology, to reconcile observations and theoretical models in a universe that is vast, complex, and filled with both immense structures and equally immense voids. The study of cosmic voids, facilitated by these algorithms, has revealed that voids are not merely empty spaces but play an active role in shaping the evolution of galaxies and the universe as a whole. Voids affect the motion of galaxies at their edges, influencing the formation of filaments and clusters. The gravitational effects of these empty regions can subtly alter the paths of nearby galaxies and contribute to the expansion of the cosmic web. By mapping voids with increasingly sophisticated methods, astronomers gain a deeper understanding of dark energy, dark matter, and the overall dynamics of the universe. The first-class density-based approach allows for a systematic and reproducible cataloguing of voids, ensuring that astronomers can compare results across different surveys and epochs. The clear boundaries identified through this method also help in modelling the interactions between voids and the surrounding cosmic structures, providing valuable insight into how these vast empty regions contribute to the evolution of the universe. On the other hand, the second-class Voronoi-based approach provides a more nuanced picture of void shapes and structures, highlighting the diversity and complexity of empty regions. Its ability to detect subvoids and smaller-scale underdense areas encourages a more detailed and hierarchical understanding of the cosmic web, revealing that voids themselves can contain intricate internal structures and can be part of larger-scale empty regions. Finally, the third-class dynamic approach goes beyond static representations of emptiness, capturing the movements of matter and the interplay between gravitational forces and dark energy. By classifying voids into true, pancake, and filament types, this method illuminates the underlying processes that give rise to the variety of void forms observed in the universe. It also allows for precise calculations of how voids evolve over cosmic time, connecting the study of empty space to fundamental cosmological parameters and the behavior of the universe on the larger scales. The historical development of these methods reflects both the growth of observational capabilities and the increasing sophistication of computational techniques in cosmology. The first-class nearest neighbour approximation, introduced in 1997, emerged at a time when large-scale galaxy surveys were becoming more comprehensive and data analysis techniques needed to keep pace. By providing a quick and standardized way to identify voids, this method laid the groundwork for systematic void catalogues, which have become invaluable tools for cosmologists. The second-class Voronoi-based methods, emerging in 2008, represented a significant conceptual shift, emphasizing geometric considerations and avoiding assumptions about void shapes. This allowed scientists to explore more realistic void forms and to study the statistical properties of voids in greater detail, although it introduced the challenge of filtering out trivial or inconsequential voids. The third-class dynamic methods, developed in 2009, marked another leap forward by integrating the physics of dark energy and gravitational displacement into void identification. This approach not only provided more precise analytical tools for studying voids, but also connected void research directly to the fundamental forces shaping the universe, offering new insights into cosmic evolution and the interaction between matter, energy, and space itself. In practical terms, researchers using the first-class density-based approach often begin by selecting galaxies from large catalogues and calculating the distance to their third closest neighbours. This process is repeated for every galaxy in the survey, creating a detailed map of local densities. Spherical cells are then expanded until the density reaches that expected for surrounding cosmic walls, allowing for a clear delineation between voids and denser regions. Overlapping voids are carefully managed, and a minimum radius of 10 megaparsecs ensures that identified voids are statistically significant. The second-class Voronoi approach, by contrast, constructs a tessellated map of space based on galaxy positions, creating cells around each galaxy and introducing mock border particles to define edges. Statistical and physical significance parameters are applied to distinguish meaningful voids from trivial ones, while subvoids are identified to understand the hierarchical nature of cosmic emptiness. The third-class dynamic approach calculates the displacement field of matter, identifying regions where matter is moving outward most strongly, and classifying voids based on their shape and dynamical properties. The three morphological classes, true, pancake, and filament voids, capture the diversity of void forms, while precise calibration of selection biases ensures reliable results. Each approach, in its own way, contributes to a more complete understanding of the universe's vast empty spaces and their relationship to the structures that surround them. Over time, the application of these void-finding algorithms has revealed patterns and phenomena that would have been difficult or impossible to detect otherwise. For example, the density-based methods highlight the surprisingly sharp boundaries of voids, where the transition from nearly empty space to dense cosmic walls occurs over relatively short distances. The Voronoi-based methods show that voids can take on highly irregular and intricate shapes, reflecting the complex interactions of galaxies and dark matter. Dynamic methods, meanwhile, reveal how voids evolve, how matter flows around them, and how different types of voids may have distinct origins and influences on cosmic structure. Together, these insights demonstrate that voids are active components of the universe, shaping the distribution of galaxies and influencing large-scale cosmic dynamics in subtle but profound ways. Through these various techniques, cosmologists are able to catalogue, analyse and interpret the emptiness of space with increasing precision and sophistication. The study of cosmic voids is not merely an academic exercise, but a vital component of understanding the universe itself, including the nature of dark matter, the influence of dark energy, and the evolution of cosmic structures over billions of years. By applying density-based geometric and dynamic methods, scientists can explore voids from multiple perspectives, uncovering patterns, relationships, and phenomena that deepen our understanding of the cosmos. Each method offers a unique lens, and together they paint a rich and detailed picture of the empty regions that are as essential to the universe as the galaxies and clusters that fill its spaces. Cosmic voids have become one of the most fascinating and insightful features in modern cosmology. These voids, although largely empty, are not entirely devoid of content. They are vast regions of space where the density of matter, particularly galaxies, is significantly lower than in the surrounding areas. In recent decades, the study of these voids has helped astronomers and cosmologists gain a deeper understanding of the universe, its structure, and its evolution over billions of years. One striking example of a cosmic void is the one in which our own Milky Way galaxy resides, known as the KBC void. This particular void, like others, has contributed significantly to refining the models that describe how the universe expands, how galaxies form, and even how mysterious forces like dark energy influence the cosmos. The presence of both the largest known voids and the largest clusters of galaxies in the universe points to a delicate balance in the composition of the cosmos. Observations indicate that approximately 70% of the total content of the universe today is made up of dark energy. This dark energy is the elusive and not yet fully understood force that drives the accelerated expansion of the universe. The existence of cosmic voids, together with massive galaxy clusters, supports this idea and aligns closely with data collected from the cosmic microwave background, the faint glow of radiation left over from the Big Bang. In other words, voids act like cosmic balloons, sensitive to the overall changes in the universe, expanding and evolving as the universe itself expands. By observing how the shape and size of these voids change over time, scientists can refine their understanding of the universe's expansion and improve models like the standard lambda cold dark matter model, often abbreviated as LCDM. In addition, these observations can help test alternative models, such as the quintessence plus cold dark matter model, known as QCDM, offering insights into the precise behavior of dark energy and how it affects the universe on both small and large scales. One of the fascinating properties of voids is their ability to reveal information about particles that are otherwise extremely difficult to study, such as neutrinos. Neutrinos are nearly massless particles that barely interact with other matter. They can travel vast distances without being affected, essentially moving freely in and out of voids. This free movement affects the size and depth of voids in the universe, and with the advancement of astronomical surveys, such as those conducted by the Euclid satellite, scientists may be able to measure the combined masses of all neutrino types. By comparing detailed observations of voids with theoretical predictions, researchers can gain valuable information about these tiny particles, whose properties influence the large-scale structure of the universe in subtle but important ways. The galaxies that inhabit cosmic voids are not simply passive objects drifting in empty space. They are part of a unique mixture of matter and energy that differs from regions of the universe that are more densely packed. In these underpopulated voids, galaxies can appear in forms that are unusual when compared to galaxies in the so-called cosmic walls or filaments, which are the dense regions connecting large clusters. This difference supports what scientists call the biased galaxy formation scenario, predicted by the Gaussian adiabatic cold dark matter model. In simple terms, this model suggests that galaxies do not form randomly, but rather in certain preferred regions depending on the surrounding density of matter. By studying the galaxies in voids, researchers can refine this picture, examining the relationships between galaxy shapes, star formation rates, and the density of their environment. For example, galaxies in voids are often younger, hotter, and more active in forming new stars. In fact, studies have shown that voids contain a significantly higher proportion of starburst galaxies, galaxies experiencing rapid periods of star formation, than galaxies located in denser cosmic structures. These observations help astronomers understand not only the conditions required for star formation, but also the broader rules that govern galaxy evolution across the universe. Voids are also invaluable tools for investigating cosmic magnetism. While the presence of magnetic fields in galaxies has been studied extensively, intergalactic magnetic fields, particularly those in the vast stretches of emptiness, remain more mysterious. In 2015, a study examined the paths of gamma rays emitted by distant blazars, extremely energetic and distant active galactic nuclei. These gamma rays travel through cosmic voids and are slightly deflected by any existing magnetic fields. By studying these deviations, scientists concluded that the intergalactic space contains magnetic fields with a strength of at least 10 to the negative 17th Gauss. The pattern and strength of these fields suggest that magnetism may have a primordial origin, existing since the very early universe, and that it may have played a crucial role in shaping magnetic fields within galaxies. Understanding these magnetic fields can also provide insights into the timeline of the universe, including periods such as recombination, when the first neutral atoms formed and light began to travel freely through space. Cosmic voids may also help explain peculiar features observed in the cosmic microwave background, CMB, the residual radiation from the Big Bang. One well-known anomaly is the so-called WMAP cold spot, detected by the Wilkinson Microwave Anisotropy probe. This region of the CMB appears colder than surrounding areas and has puzzled scientists since its discovery. Some researchers suggest that the cold spot could be the result of an enormous cosmic void, with a radius of approximately 120 megaparsecs, lying along the line of sight between Earth and the early universe. When the late integrated Sachs-Wolf effect, an effect related to the stretching of light in an expanding universe, is taken into account, the presence of such a void could partially explain these cold spots. As a result, cosmic voids offer a potential solution to some of the more puzzling observations in cosmology, showing how even the emptiest regions of space can leave measurable imprints on the universe. While dark energy is currently the leading explanation for why the universe is expanding at an accelerating rate, some alternative theories have been considered. One such idea suggests that if our galaxy is situated within an unusually large, not-so-dense cosmic void, this could create the illusion of acceleration, reducing or even eliminating the need to invoke dark energy. Although more recent data have reduced the likelihood of this scenario as a complete replacement for the standard LCDM model, the possibility has not been entirely dismissed. Studying voids in detail, therefore, provides a complementary approach to understanding cosmic acceleration and testing different cosmological hypotheses. In addition to testing models of dark energy, the number and distribution of cosmic voids, particularly when combined with the study of galaxy clusters, provides a powerful tool for probing the fundamental laws of physics on cosmic scales. By observing voids in low-density regions of the universe and comparing them to dense clusters, scientists can perform precision tests of general relativity and explore whether any deviations occur in underpopulated areas. Voids act as natural laboratories for such studies because the gravitational interactions inside them are often much weaker than in denser regions, allowing researchers to test theories with fewer complicating factors. The interiors of voids often appear to follow a slightly different set of cosmological parameters than the rest of the universe. This difference makes voids especially useful for understanding the effects of gravitational clustering and growth rates on local galaxies. Because voids are underdense, the interactions between particles and galaxies within them are minimal compared to those in denser regions, allowing scientists to study the evolution of structures in a nearly isolated environment. Larger voids, in particular, tend to remain in a linear regime, where their structures maintain a roughly spherical shape and the dynamics inside are relatively simple. This contrasts with denser regions, where gravitational interactions create complex patterns of clustering and merging. By studying voids, cosmologists can test models with high precision and explore variations in parameters such as the matter density, denoted as omega sub m, the dark energy density, omega sub lambda, and the Hubble constant, h0, which describes the rate of expansion of the universe. Furthermore, cosmic voids are more than just empty gaps between galaxies. They are dynamic regions where subtle processes shape the distribution of matter and influence the evolution of nearby galaxies. Within voids, galaxies can interact in unique ways. While the interactions are less frequent due to the lower density of matter, the processes that do occur can differ significantly from those in denser regions. The underdense environment allows galaxies to retain more of their original characteristics, providing astronomers with a glimpse into conditions that may resemble the early universe. This makes voids especially valuable for studying galaxy morphology, star formation rates, and the effects of local gravitational environments on the growth and evolution of cosmic structures. The abundance and distribution of voids across the universe also provide key information about large-scale structure formation. Voids are not randomly scattered, but instead form an intricate network interwoven with filaments and walls of galaxies, creating what scientists call the cosmic web. The cosmic web is the large-scale skeleton of the universe, with dense clusters forming the nodes, filaments acting as bridges, and voids filling the spaces in between. By mapping the size, shape, and distribution of voids, astronomers can better understand the processes that lead to the formation of the cosmic web and the interactions between galaxies and dark matter. These observations are also useful for testing the predictions of theoretical models, providing a feedback loop between observation and theory that drives the field forward. Voids can also influence the types of galaxies they contain. In particular, observations indicate that void galaxies often have different morphological and spectral properties compared to those in denser cosmic structures. They are more likely to be small, blue, and rich in gas, which allows them to continue forming new stars at higher rates. This contrasts with galaxies in denser environments, where interactions and mergers tend to accelerate the aging process, producing redder, more elliptical galaxies with less ongoing star formation. The differences between void galaxies and wall galaxies illustrate how environment plays a crucial role in shaping galaxy evolution, highlighting the importance of studying under dense regions to understand the full diversity of galaxy properties. In addition to their importance for galaxy formation studies, voids are increasingly recognized as valuable tools for probing fundamental physics. Their sensitivity to cosmological parameters and their relatively simple internal dynamics make them ideal for testing alternative theories of gravity, the behavior of dark energy, and even the properties of neutrinos. Future surveys and space missions, such as the European Space Agency's Euclid satellite, are expected to provide unprecedented data on voids, allowing researchers to perform detailed statistical analyses that can constrain the masses of neutrinos, the behavior of dark energy, and the validity of general relativity on cosmic scales. The unique combination of emptiness, simplicity, and sensitivity to cosmic parameters ensures that voids will continue to be a rich field of study for decades to come. The study of voids also intersects with the examination of cosmic magnetic fields. Magnetic fields in the universe are not only confined to galaxies, but extend throughout intergalactic space. Measuring these fields is challenging, but voids provide an environment where the effects of magnetism can be isolated and studied. The deflection of gamma rays from distant sources, as observed in 2015, has provided a lower bound on the strength of intergalactic magnetic fields, indicating that even the vast emptiness of space is threaded with magnetism. These fields may have originated in the early universe and could have influenced the formation and evolution of galaxies, stars, and other structures. Understanding their origin and properties can shed light on some of the earliest moments of cosmic history, linking the study of voids to fundamental questions about the origin and evolution of the universe itself. Voids also offer insights into anomalies in the cosmic microwave background. As mentioned, cold spots in the CMB, such as the WMAP cold spot, may be explained by the presence of enormous voids along the line of sight. These voids can cause slight shifts in the energy of photons as they travel through underdense regions, creating observable effects in the radiation that has been traveling across the universe for billions of years. By carefully mapping these voids and modeling their impact on light propagation, scientists can better understand the subtle interactions between matter, radiation, and the large-scale structure of the universe. In addition to providing constraints on cosmology, the study of voids allows researchers to explore how galaxies evolve in isolation. Galaxies in voids often develop more slowly, retaining more gas and continuing to form stars over longer periods. This contrasts with galaxies in dense environments, where gravitational interactions, mergers, and feedback processes can strip gas and suppress star formation. By comparing void galaxies to those in walls and clusters, astronomers can gain a more complete picture of galaxy evolution, disentangling the effects of environment from intrinsic properties. Another fascinating aspect of voids is their potential to test deviations from standard models of gravity. Since gravitational interactions are weaker in underdense regions, voids serve as natural laboratories for examining whether general relativity holds in all environments or whether modifications are needed at large scales. By measuring the shapes, sizes, and distribution of voids and comparing them with predictions from different theories, scientists can test the limits of our understanding of gravity and explore alternative scenarios for cosmic evolution. Voids provide a unique perspective on the overall structure of the universe. While dense clusters and filaments dominate visually striking features, the emptiness of voids is equally important. They form the backbone of the cosmic web, shaping the distribution of matter and influencing the motion of galaxies. Studying voids helps scientists understand the balance between structure and emptiness, the interplay of forces such as gravity and dark energy, and the dynamic evolution of the cosmos over billions of years. The emptiness itself becomes a powerful tool, offering insights that cannot be obtained from studying only the denser regions of the universe. The universe in all its vastness is an almost unimaginable expanse of galaxies, stars, planets, and mysterious cosmic phenomena, but hidden among the luminous clusters and sparkling nebulae lie regions of astonishing emptiness. These are the voids of the universe, enormous stretches of space where galaxies are extremely scarce or entirely absent. They are not merely gaps or empty patches in the cosmic web, but immense, fascinating structures that stretch across millions of light years, challenging our understanding of how the cosmos is organized and how it has evolved over billions of years. Among these voids, some are so immense that they defy our ordinary perception of scale, dwarfing even the grandest known galaxies and galaxy clusters. When we attempt to define the biggest void in the universe, we are venturing into a realm where size and emptiness reach extremes that are almost impossible to imagine. These voids are vast, silent regions where the familiar clumps of stars and galaxies that we associate with the night sky are nearly non-existent, and their enormity helps scientists explore fundamental questions about the nature of the universe, including its expansion, its composition, and the mysterious forces that govern it. The largest known voids are cosmic anomalies, regions that can extend across hundreds of millions of light years, and they are often identified through meticulous mapping of the distribution of galaxies across the sky. The sheer scale of these voids is such that if one were to travel through them, the journey could last for tens of millions of years at the speed of a light, and yet one might encounter only a handful of galaxies, if any at all. These voids are often bounded by intricate networks of filaments and walls, massive structures made of clusters of galaxies that trace the large-scale structure of the universe. These filaments act as cosmic highways, where galaxies and matter flow and gather, leaving behind enormous pockets of emptiness. Scientists describe this structure as the cosmic web, with voids serving as the vast open spaces between the dense threads. Unlike the filaments and walls, which are vibrant and filled with the light of countless stars, the voids appear almost lifeless, dark, and still, their presence inferred more from absence than from observable matter. One of the most fascinating aspects of these immense voids is how they are discovered and measured. Astronomers and cosmologists rely on surveys of galaxies, such as those conducted over the past few decades with increasingly powerful telescopes and instruments. By mapping the positions of hundreds of thousands or even millions of galaxies, scientists can identify regions where galaxies are notably missing or significantly fewer than expected. These empty zones are then analysed for their size, shape, and the distribution of any galaxies within them. The largest voids are often not perfectly spherical. Instead, they may appear elongated, irregular, or somewhat lumpy, reflecting the complex gravitational interactions that have shaped the cosmic web over billions of years. The process of defining a void is not as simple as marking an empty space, because even within these immense regions, tiny galaxies or small clusters can exist, lingering like isolated islands in an ocean of near-nothingness. Among the largest and most studied voids in the universe is the one known as the KBC void. This enormous void is named after the initials of the researchers who identified it, and it is believed to encompass a region several billion light-years across. To put this into perspective, the Milky Way galaxy, home to our solar system, is a relatively small spiral galaxy measuring about 100,000 light-years across. This means that the KBC void could contain enough space to fit millions of galaxies the size of the Milky Way and still have room left over. Yet within its boundaries, galaxies are extremely sparse. Our own Milky Way galaxy is located on the outskirts of this void, which has implications for observations of cosmic expansion and the measurement of the Hubble constant, the rate at which the universe is expanding. By studying the KBC void, astronomers gain insights into the behavior of dark energy, the mysterious force that drives the acceleration of cosmic expansion, and into how large-scale structures evolve over time. Another extraordinarily large void, often discussed in scientific literature, is the Boötes Void, located in the direction of the constellation Boötes. This void is estimated to span about 300 million light-years, an unimaginable distance when compared to the scale of individual galaxies. When the Boötes Void was first discovered in 1981, it astonished scientists because it contained only a few dozen galaxies, in a volume where thousands would normally be expected. To imagine this, picture a spherical region so vast that it could theoretically hold 1,000 Milky Way-sized galaxies and yet remain almost entirely empty. The discovery of the Boötes Void challenged prior assumptions about the uniformity of the universe on large scales and spurred a wave of research into how such enormous empty regions could form. It is thought that these voids arise from the gravitational pull of surrounding structures, where matter is drawn toward denser regions, leaving behind immense pockets of near emptiness. Over billions of years, these processes magnify the voids, creating the enormous cosmic gaps we observe today. In addition to the KBC void and the Boötes Void, there are other notable large voids that contribute to our understanding of cosmic emptiness. The Eridanus supervoid, for instance, is a massive underdense region that spans approximately 1 billion light-years across. This void is of particular interest because it coincides with the cold spot in the cosmic microwave background, the faint afterglow of the Big Bang. The alignment between this enormous void and the cold spot suggests that large voids can influence the distribution of radiation in the universe, potentially causing measurable anomalies in cosmic observations. Scientists hypothesize that the lower density of matter within such a void can slightly alter the path of cosmic radiation, producing observable effects that help us probe the nature of cosmic expansion and the large-scale distribution of matter. These connections between enormous voids and other cosmological phenomena illustrate how studying emptiness can provide profound insights into the workings of the universe. The formation of these gigantic voids is closely tied to the history of the universe itself. After the Big Bang, approximately 13,800 million years ago, matter was not evenly distributed. Tiny fluctuations in density allowed regions with slightly more matter to attract even more matter through gravity, eventually forming galaxies, clusters, and filaments. Conversely, regions with slightly less matter became emptier over time, as the gravitational pull of surrounding denser regions drew matter away. These underdense regions expanded with the universe, growing larger and emptier, forming the voids that we observe today. The scale of these voids reflects the interplay between cosmic expansion, gravity, and the initial distribution of matter in the early universe. Their existence is a testament to the incredible vastness of the cosmos and the subtle, almost invisible forces that shape its structure over billions of years. One particularly intriguing characteristic of these massive voids is how they challenge our perception of matter and energy. Despite appearing empty, voids are not entirely devoid of matter. Extremely sparse, diffuse gas and dark matter may still exist within them, spread thinly across immense distances. The behavior of this matter differs from that in denser regions. For instance, galaxies within voids may evolve differently due to the lower frequency of interactions and mergers. Some studies suggest that isolated galaxies within voids may continue to form stars more slowly, or may retain more pristine characteristics compared to galaxies in crowded clusters. Additionally, voids are thought to be influenced by dark energy in a more pronounced way, since their low density allows the accelerating expansion of space to have a more noticeable effect. By observing voids, astronomers can gain unique perspectives on how dark energy operates across different regions of the universe, providing clues to one of the greatest mysteries in modern cosmology. Observational techniques for studying voids have advanced dramatically over the past few decades. Large-scale galaxy surveys, such as the Sloan Digital Sky Survey and others, have mapped the positions of millions of galaxies across the sky, revealing the intricate network of filaments, walls, and voids that form the cosmic web. By analysing the distribution of galaxies, astronomers can identify voids, measure their size, and study their internal structure. Computer simulations of cosmic evolution also play a critical role, allowing scientists to model the growth of voids over billions of years. These simulations take into account gravity, dark matter, and dark energy, predicting how voids expand and how galaxies evolve in different environments. Comparing these predictions with observational data helps refine models of cosmology and improves our understanding of the fundamental forces shaping the universe. While voids may seem like regions of emptiness and quiet, they are far from simple. The edges of voids, where they meet denser filaments and walls, are regions of intense gravitational interaction. Matter flows outward from the voids and inward toward the filaments, creating dynamic movements of galaxies and gas. In some cases, small clusters of galaxies can form along the boundaries of voids, creating a stark contrast between the near-empty interior and the crowded edges. These boundary effects make voids important laboratories for studying the interplay between density, gravity, and cosmic evolution. They also serve as natural experiments for testing theories about how galaxies form and evolve in different environments, providing insights that cannot be obtained by studying only dense regions of the universe. The scale of the largest voids is difficult to convey in human terms. To imagine a void like the KBC void, which extends across billions of light-years, one must think of distances far beyond everyday comprehension. 1 light-year, the distance light travels in 1 year, is already nearly 6 trillion miles, or roughly 10 trillion kilometers. Multiply this by hundreds of millions or billions, and the resulting distances become almost inconceivable. These voids are vast enough to encompass countless galaxies, yet they contain very few, making them extraordinary cosmic features. Even more remarkable is that despite their emptiness, they influence the universe around them, affecting the motion of galaxies, the distribution of cosmic radiation, and the behavior of dark energy on large scales. Some of the most profound questions about voids concern their role in the evolution of the universe. Why do some regions become so empty, while others accumulate enormous amounts of matter? How do voids grow and evolve over billions of years? How do they interact with surrounding structures, and what can they reveal about the mysterious forces that govern cosmic expansion? By studying voids, astronomers can probe the underlying physics of the universe, test models of dark energy and dark matter, and explore the earliest moments of cosmic history. Observations of voids have also led to unexpected discoveries, such as unusual galaxies that appear isolated in these vast empty regions, or subtle variations in cosmic radiation that correlate with the presence of enormous voids. Each new observation adds a piece to the puzzle of the universe, showing that even emptiness can be full of meaning and significance. Voids are not merely passive features of the cosmos, they actively shape the universe on large scales. Their low-density interiors expand faster than the surrounding denser regions, contributing to the complex pattern of cosmic expansion. Galaxies near voids may experience different gravitational influences compared to those in clusters or filaments, affecting their motion and evolution. The interplay between voids and surrounding structures also influences the formation of cosmic flows, the large-scale movement of galaxies through space. In this way, voids are integral components of the cosmic web, essential for understanding the dynamics of the universe and the forces that shape it over billions of years. Interestingly, voids can also serve as natural laboratories for studying the properties of galaxies in isolation. Galaxies within voids are less likely to collide or merge with others, allowing astronomers to study how galaxies evolve in the absence of frequent interactions. These galaxies may retain more primordial characteristics, providing insights into the conditions of the early universe. By comparing void galaxies with those in denser regions, scientists can investigate how environment affects galaxy formation, star formation rates, chemical composition, and the development of galactic structures such as spiral arms or central bulges. The study of void galaxies has revealed a remarkable diversity of forms and behaviors, demonstrating that even in the sparsest regions of the cosmos, the processes of cosmic evolution continue in complex and fascinating ways. Some voids have gained attention not only for their size, but also for the peculiar effects they have on surrounding cosmic phenomena. For example, The Eridanus supervoid has been linked to anomalies in the cosmic microwave background, the faint glow left over from the Big Bang. The presence of such an enormous underdense region can slightly alter the energy of cosmic radiation passing through it, producing subtle but measurable effects. Observing these effects allows scientists to test theoretical models of cosmic expansion, energy distribution, and the influence of dark matter and dark energy. These connections highlight the profound importance of studying voids, demonstrating that even regions that appear empty can have measurable consequences for the universe as a whole. Throughout the history of astronomy, voids have challenged assumptions about the homogeneity and uniformity of the cosmos. Early models of the universe often assumed that, on large scales, matter was evenly distributed. The discovery of massive voids revealed that the universe is far more complex, with vast regions of emptiness interspersed with dense filaments, clusters, and superclusters. These discoveries have reshaped our understanding of cosmic structure, illustrating that the large-scale universe is not simply a random scattering of galaxies, but a carefully organized web of matter and emptiness, shaped by gravity, expansion, and the mysterious forces of dark matter and dark energy. The identification of voids, their measurement, and their study have become central to modern cosmology, providing crucial insights into the origin, evolution, and large-scale architecture of the universe. In addition to their scientific significance, voids also capture the imagination because of the philosophical and existential questions they raise. They are vast cosmic regions almost entirely devoid of galaxies, stars, and planets, offering a stark contrast to the richness of the visible universe. In contemplating these enormous empty spaces, one is reminded of the immense scales of the cosmos and the relative insignificance of familiar objects like stars, planets, and even entire galaxies. Voids provide a sense of perspective, illustrating the immensity and mystery of the universe and inviting reflection on the forces and processes that shape it. They are silent, dark, and almost otherworldly, yet they are integral to the structure and evolution of the cosmos. The largest known voids, such as the KBC void, the Boötes Void, and the Eridanus supervoid, serve as natural laboratories for exploring fundamental questions about the universe. They help scientists study the nature of dark energy, the influence of dark matter, the behavior of galaxies in isolation, and the evolution of cosmic structures over billions of years. Their vast emptiness contrasts with the dense clusters and filaments that surround them, providing a unique perspective on the cosmic web. Through careful observation, mapping, and computer simulations, astronomers continue to uncover the secrets of these colossal voids, revealing the dynamic interplay between emptiness and structure, isolation and interaction, stillness and motion. These voids demonstrate that even the vastest emptiness in the universe is filled with meaning, influence, and significance, shaping the cosmos in ways that are only beginning to be understood. Even as scientists study voids in greater detail, new discoveries continue to emerge. Advances in telescope technology, sky surveys, and computational modeling enable increasingly precise mapping of the cosmic web and the voids within it. Each new measurement reveals additional details about the size, shape, and structure of these empty regions, as well as their impact on surrounding galaxies and cosmic radiation. The study of voids is a continually evolving field, reflecting the broader progress of astronomy and cosmology in understanding the universe on the largest scales. As our observational capabilities improve, we can expect to discover even larger and more complex voids, offering new insights into the forces and processes that govern the cosmos. At the heart of the study of the biggest voids is the recognition that emptiness is not a simple absence, but a phenomenon with its own structure, dynamics, and influence. Voids are shaped by the same forces that shape the rest of the universe, including gravity, dark matter, and dark energy, and their evolution reflects the interplay of these forces over billions of years. They are empty, yet dynamic, vast, yet structured, simple, yet complex. By examining voids, scientists gain not only a better understanding of cosmic structure, but also a deeper appreciation for the intricate and interconnected nature of the universe. Voids remind us that even emptiness can hold mysteries, that absence can have effects, and that the universe is a tapestry woven from both matter and space, presence and void. Throughout decades of research, astronomers have catalogued and analysed many of the largest known voids, each with unique characteristics and significance. The Boötes Void, discovered in 1981, remains a landmark in the study of cosmic emptiness, astonishing in its scale and sparseness. The KBC Void, encompassing our Milky Way galaxy, has provided critical insights into the measurement of cosmic expansion and the behavior of dark energy. The Eridanus supervoid has illuminated the relationship between underdense regions and anomalies in cosmic radiation. Each of these voids, along with countless smaller ones scattered across the universe, contributes to our understanding of how cosmic structure arises, evolves, and interacts. They exemplify the extraordinary scales and forces at play in the universe, and they offer endless opportunities for exploration, observation, and discovery. Voids challenge our intuition, because they are regions of space that are not merely empty in the conventional sense, but profoundly underdense compared to the surrounding cosmic web. Their discovery has reshaped cosmology, revealing that the universe is not uniformly filled with galaxies, but is a complex mosaic of dense filaments and enormous empty regions. Observing and studying voids requires careful mapping, precise measurements, and sophisticated modeling, but the insights gained are invaluable. By examining the distribution of galaxies, the behavior of radiation, and the dynamics of isolated matter, scientists can probe fundamental questions about the universe, from its earliest moments to its long-term evolution. Voids are more than just gaps in space. They are active participants in the cosmic story, shaping the motion of galaxies, influencing cosmic expansion, and revealing the subtle forces that govern the universe. The study of the largest voids also informs our understanding of the Milky Way's place in the universe. Being located on the edge of the KBC Void, our galaxy provides a unique vantage point for observing the effects of underdense regions on local cosmic structures. The presence of such a vast void nearby affects the distribution of galaxies, the measurement of cosmic expansion, and the interpretation of astronomical observations. By analysing the Milky Way's environment in relation to the KBC Void, scientists can refine models of cosmic evolution, test theories of dark energy, and better understand the processes that govern galaxy formation. This connection between our galaxy and a colossal cosmic void underscores the intricate relationships that exist throughout the universe, where even vast emptiness can have profound consequences for nearby structures. In addition to their scientific significance, voids capture the imagination because of their sheer scale and mystery. They are enormous, silent, and dark, yet they are fundamental components of the cosmic web. Each void, whether the Boötes Void, the KBC Void, the Eridanus supervoid, or countless others, represents a frontier of discovery, a region where the familiar rules of galaxy clustering are stretched to extremes, and where the interplay of cosmic forces can be studied in isolation. By exploring these immense empty regions, scientists and observers alike are drawn into a deeper understanding of the universe, a realization that emptiness is not mere absence, but a key player in cosmic evolution. These voids, in their immense silence, speak volumes about the history and structure of the cosmos, and studying them reveals patterns and behaviors that are otherwise hidden in the crowded and bright regions of galaxies and clusters. Even within the vast emptiness of the largest voids, subtle structures can exist. Small filaments of galaxies, isolated dwarf galaxies, or faint clouds of gas and dust may weave through the void, almost like threads of life persisting in the most unlikely environments. These rare structures provide scientists with laboratories for understanding how galaxies can form and survive in extreme isolation. Observations of such galaxies show that they can differ significantly from their counterparts in denser regions. They may have less frequent star formation, less heavy element enrichment, and fewer collisions with other galaxies, allowing them to retain a more primordial state. In this sense, void galaxies are time capsules, preserving conditions that were more common in the early universe, and offering scientists unique windows into galactic evolution across cosmic time. The largest voids are not static. They evolve as the universe expands. The expansion of space itself, accelerated by dark energy, stretches the underdense regions, making them larger and emptier over time. Surrounding filaments and walls of galaxies gradually pull matter away from the voids, enhancing their emptiness and reshaping their boundaries. This dynamic evolution affects not only the voids themselves, but also the motion of galaxies in neighbouring regions, creating patterns of cosmic flows that can be traced across millions of light years. By studying these motions, astronomers can infer the distribution of matter, including dark matter, and test cosmological models that describe how the universe has evolved since the Big Bang. The influence of voids extends beyond matter to radiation. For example, the cosmic microwave background, the afterglow of the Big Bang, can be subtly affected by the presence of massive voids. As radiation passes through a void, the slight underdensity of matter can cause changes in the temperature and energy of photons, producing observable anomalies. These effects are small, but measurable with precise instruments, and they provide a remarkable link between the largest empty regions of the universe and the faintest traces of its earliest moments. The Eridanus supervoid, for instance, coincides with a cold spot in the cosmic microwave background, suggesting that voids may have detectable impacts even across the vast reaches of space and time. Understanding the formation of these enormous voids requires an appreciation of cosmic history. From the very beginning, the universe was not perfectly uniform. Tiny fluctuations in density, present even in the first moments after the Big Bang, were amplified by gravity. Regions slightly denser than average pulled in more matter, while slightly underdense regions lost matter to their denser neighbours. Over billions of years, these initial imbalances led to the formation of the cosmic web, dense filaments, clusters, and superclusters surrounding vast, nearly empty voids. The growth of voids is a natural consequence of these gravitational processes combined with cosmic expansion. The largest voids, with scales of hundreds of millions to billions of light-years, are thus direct evidence of the universe's early conditions and the forces that have shaped it throughout its history. In mapping and defining these voids, astronomers rely on both observation and simulation. Large-scale galaxy surveys, such as the Sloan Digital Sky Survey, have catalogued the positions of millions of galaxies, revealing the intricate lattice of filaments and voids that form the cosmic web. At the same time, computer simulations that model the evolution of matter under gravity, dark matter, and dark energy allow scientists to predict the formation and growth of voids over billions of years. By comparing simulations with observations, researchers can refine their understanding of cosmic evolution, test theories of dark energy, and investigate the interplay between matter and emptiness on the larger scales. These studies reveal that even regions that appear empty are influenced by the same fundamental forces that govern the distribution and motion of galaxies throughout the universe. The KBC void, the Boötes Void, and the Eridanus supervoid are just a few examples of the extraordinary scale and complexity of the largest known voids. The KBC void, for instance, is so vast that it could contain our Milky Way galaxy and billions of similar galaxies within its boundaries, yet remains largely devoid of them. The Boötes Void, spanning approximately 300 million light-years, challenged assumptions about the uniformity of the universe when it was discovered in 1981. The Eridanus supervoid, extending over nearly 1 billion light-years, interacts in fascinating ways with cosmic radiation, providing observable evidence of the influence of underdense regions on the universe at large. Each of these voids is a testament to the dynamic and intricate processes that govern cosmic evolution, demonstrating that emptiness is an integral part of the cosmic story. Voids also highlight the importance of perspective in understanding the universe. Observing galaxies and clusters or filaments reveals much about interactions, mergers, and the evolution of dense structures, but studying voids shows how galaxies can evolve in isolation. By contrasting these environments, scientists gain a fuller picture of galactic formation and evolution. Galaxies in voids may be smaller, less complex, and slower to form new stars, yet they retain properties that offer clues about the early universe. This interplay between emptiness and density, isolation and interaction, provides a nuanced understanding of how the cosmos has evolved over billions of years. The edges of voids are regions of particular interest. At these boundaries, the transition from near emptiness to dense clusters occurs over vast distances, and matter flows from the void into the surrounding filaments. This flow of matter shapes the large-scale motion of galaxies, producing patterns that can be observed and measured. The study of these flows reveals information about the distribution of both visible matter and dark matter, helping scientists refine models of cosmic structure and evolution. Boundaries also highlight the contrast between void interiors and surrounding regions, illustrating the dynamic nature of the universe even in places that appear to be empty and still. Voids are also important in understanding the nature of dark energy. Because voids are underdense, the accelerating expansion of the universe driven by dark energy has a more pronounced effect within them. Studying how voids expand and how their boundaries interact with surrounding matter allows astronomers to test theories of dark energy and to explore its influence on the universe over billions of years. The behavior of voids under cosmic expansion provides a unique window into one of the most mysterious forces in modern cosmology, offering insights that cannot be obtained by observing only dense clusters of galaxies. As technology and observational capabilities improve, our understanding of voids continues to deepen. New surveys, telescopes, and instruments allow for more precise mapping of the cosmic web, revealing the size, shape, and structure of voids in unprecedented detail. Observations of faint galaxies within voids, subtle flows of matter along their boundaries, and interactions with cosmic radiation provide increasingly rich datasets for analysis. At the same time, increasingly sophisticated computer simulations allow scientists to model the evolution of voids with greater accuracy, incorporating complex physics and interactions over cosmic timescales. These advances promise to expand our understanding of voids, their role in cosmic evolution, and their influence on the universe as a whole. The presence of enormous voids also invites reflection on the sheer scale of the universe. Distances measured in hundreds of millions or billions of light-years surpass ordinary human comprehension, and yet these voids exist as real, observable features of the cosmos. Considering their size, it is remarkable that even a galaxy as massive and luminous as the Milky Way appears almost inconsequential in comparison. The study of voids emphasizes the vastness of space and the delicate balance of forces that govern the structure of the universe. Voids are reminders that the cosmos is not only populated by dazzling galaxies and bright stars, but also shaped by immense regions of near emptiness that influence the distribution and motion of matter on the larger scales. Even as we study voids, they remain sources of mystery and wonder. Their size, scale, and influence continue to challenge our understanding of cosmology and the forces that shape the universe. Each void is unique, with its own shape, size, and internal structures, and each interacts differently with surrounding filaments, clusters, and cosmic radiation. Observations continue to uncover new and surprising details, from isolated galaxies within voids to subtle distortions in cosmic background radiation. These discoveries reveal that voids are far from uniform or simple. They are dynamic regions with complex internal behaviors, shaped by gravity, cosmic expansion, and the invisible forces of dark matter and dark energy. In contemplating the largest voids, one realizes that emptiness is not merely a passive backdrop for cosmic activity. Instead, it is an active, dynamic component of the universe, influencing galaxy formation, matter distribution, cosmic expansion, and even radiation patterns. The study of voids complements the study of dense structures, providing a fuller and richer understanding of the cosmic web. The enormous voids, including the KBC void, the Boötes Void, and the Eridanus supervoid, reveal the extraordinary scale, complexity, and subtlety of the universe. They demonstrate that emptiness can have structure, influence, and significance, shaping the universe in ways that are not immediately visible but profoundly important. As mapping techniques improve and simulations become more precise, the study of voids will likely uncover even larger and more complex structures, offering new insights into the fundamental forces that govern the universe. Observations of voids continue to refine measurements of the Hubble constant, provide evidence for the influence of dark energy, and reveal the evolution of galaxies in extreme isolation. Even the smallest features within a void, such as faint dwarf galaxies or thin streams of gas, provide clues about the early universe and the processes that shape cosmic evolution. By studying voids, scientists explore a realm of space where absence reveals as much as presence, and where silence speaks volumes about the forces shaping the cosmos. The largest voids are also a reminder of the intricate balance of the universe. While dense clusters and filaments draw matter together, voids push it apart, creating a cosmic equilibrium that extends across billions of light-years. This interplay between matter and emptiness, attraction and expansion, is fundamental to the structure and evolution of the cosmos. Voids influence the motion of galaxies, the flow of matter, and the propagation of radiation, and they provide natural laboratories for testing cosmological theories under conditions very different from dense clusters. Through these studies, scientists gain a more complete understanding of how the universe works on the larger scales, revealing the subtle and profound effects of emptiness in shaping the cosmos. Even with decades of research, the largest voids remain a frontier of discovery. Their scale and complexity challenge our understanding of cosmic evolution, while their subtle influence on matter and radiation offers opportunities for new insights. Each void is a testament to the forces that have shaped the universe over billions of years, from the initial fluctuations after the Big Bang to the ongoing expansion driven by dark energy. Observing and studying these voids allows scientists to probe the universe in a unique way, exploring regions where galaxies are few, matter is sparse, and emptiness dominates. In doing so, they uncover information about the structure, history, and evolution of the cosmos, revealing that even the vastest voids are filled with meaning and significance. The interplay between voids and the surrounding cosmic web also provides insights into the evolution of galaxy clusters and superclusters. As voids expand and matter flows outward, dense regions are shaped and reshaped, influencing the development of massive galaxy clusters and the formation of filaments that connect them. These interactions demonstrate that voids are not isolated features, but integral parts of the cosmic ecosystem, affecting structures and dynamics across immense distances. By studying voids, astronomers can better understand the processes that create the large-scale patterns of the universe, including the distribution of dark matter, the behavior of cosmic flows, and the influence of dark energy on cosmic expansion. When people first began to map the universe on a grand scale, they imagined that galaxies were sprinkled almost evenly through space, like stars in the night sky. But as telescopes became more powerful, and astronomers started measuring the positions of millions of galaxies, they discovered something entirely different. The universe was not a smooth sea of matter at all. Instead, it looked like a vast web made up of bright threads, knots, and enormous empty regions. These bright threads are called filaments, and they are filled with galaxies, clusters, and superclusters. The empty regions between them are known as cosmic voids, and they make up most of the volume of the universe. To understand the sheer scale of these voids, it helps to imagine the structure of the cosmos as a gigantic sponge or a three-dimensional web. The filaments form the solid parts, and the voids are the bubbles in between. Galaxies, clusters, and superclusters make up the densest areas of this structure, while the voids represent the thinnest parts, regions where matter is stretched so thin that sometimes there may be only a few lonely galaxies floating across hundreds of millions of light-years of space. When astronomers talk about a galaxy, they are describing an island of stars, gas, dust, and dark matter held together by gravity. Our own Milky Way is one of these vast systems, containing hundreds of billions of stars and stretching about 100,000 light-years from side to side. To put that in perspective, light takes 100,000 years to travel from one end of our galaxy to the other. That might sound huge, but in cosmic terms, even the Milky Way is a small part of something much greater. Galaxies rarely exist alone. They are usually found grouped together in what scientists call clusters. A cluster of galaxies is a collection of dozens, hundreds, or even thousands of galaxies bound together by gravity. One of the closest large clusters to us is the Virgo cluster, located about 55 million light-years away. It contains around 2,000 galaxies, all orbiting within a common center of gravity. Clusters like Virgo are the building blocks of even larger structures called superclusters. Superclusters are colossal formations made up of many galaxy clusters linked together by long, thin filaments of galaxies. The supercluster that our Milky Way belongs to is known as the Laniakea supercluster. It stretches across more than 500 million light-years and contains around 100,000 galaxies. The name Laniakea comes from the Hawaiian language and means immense heaven, a fitting description for something of such magnitude. Now, imagine that within this grand cosmic web, there are immense spaces where almost nothing exists. These are the cosmic voids. A typical void might measure tens or even hundreds of millions of light-years across. That means that from one side of a void to the other, light could take hundreds of millions of years to travel, even though it moves at nearly 300,000 kilometers every second. These vast regions are not just empty of stars and galaxies, they are nearly devoid of all matter, including dark matter, which makes up most of the mass in the universe. The largest known voids dwarf even the most massive galaxy clusters and superclusters. One of the most famous examples is the Boötes Void, discovered in the year 1981 by astronomer Robert Kirshner and his team. It lies in the direction of the constellation Boötes and is sometimes called the Great Nothing. The Boötes Void spans nearly 330 million light-years across, making it one of the largest known structures of emptiness in the universe. If the Milky Way were placed at the centre of the Boötes Void, it would take light more than 300 million years to reach the edge. Inside this enormous volume, only a few dozen galaxies have been found. To compare, in a typical region of the same size within a filament, there would be tens of thousands of galaxies. When scientists first discovered the Boötes Void, they were astonished. It was far emptier than anyone had expected. According to models of the universe that were popular at the time, such a massive and nearly empty region should not exist. Yet it did. That discovery forced cosmologists to reconsider how the universe's large-scale structure had formed. Over time, computer simulations of cosmic evolution, based on the effects of gravity, dark matter, and dark energy, began to reproduce similar voids, showing that they could arise naturally as galaxies and matter were drawn into filaments and clusters, leaving behind empty bubbles. To grasp the difference in scale between galaxies, clusters, superclusters, and voids, imagine starting with something familiar, the Milky Way. If the Milky Way were represented by a single small dot on a page, the distance to the nearest large galaxy, the Andromeda Galaxy, would be about 2.5 million light-years, or in our drawing just a few centimetres away. A typical cluster, like the Virgo cluster, would fill a space equivalent to a large sheet of paper, but a supercluster like Laniakea would stretch across the length of several rooms. In comparison, a void like the Boötes Void would be so large that it could swallow not just the entire Laniakea supercluster, but dozens more like it, and still have room left over. These voids are not just empty holes in space. They are important features that help shape the universe as we know it. They influence how galaxies move, how light travels, and how the universe expands. For instance, galaxies near the edges of voids feel a gravitational pull toward the denser regions, the filaments and clusters, causing them to drift away from the centers of voids. This process makes the voids expand even more over time, growing emptier and larger as billions of years pass. Scientists studying cosmic voids have realized that they provide unique laboratories for testing our understanding of the universe. Because voids are relatively free from the complexities of dense matter, they act as clean regions where researchers can study the influence of dark energy, the mysterious force that is causing the universe's expansion to accelerate. The way voids grow and evolve can reveal clues about the strength and nature of dark energy, as well as the properties of gravity on the larger scales. If one were to take a map of the observable universe, which stretches roughly 93 billion light-years from one end to the other, one would see that galaxies and clusters form long filaments that weave through enormous bubbles of nothingness. These bubbles, or voids, make up about 80% of the total volume of the universe, even though they contain less than 10% of its matter. That means most of the cosmos, by volume, is almost completely empty. Comparing this vast emptiness to the structures we know gives us a sense of awe. Our Milky Way, with its hundreds of billions of stars, might feel enormous, but it is only one small spark in a filament of the Laniakea supercluster. That filament itself is merely one strand of the cosmic web that borders immense voids. Inside those voids, a traveller could journey for hundreds of millions of years at the speed of light and see almost nothing but darkness, perhaps encountering an occasional faint galaxy drifting alone. In these enormous empty spaces, the density of matter is so low that it's almost beyond human imagination. In a typical region of the universe, there might be one atom in every cubic meter of space. But inside a large cosmic void, that number drops drastically, perhaps to one atom in every 10 cubic meters, or even less. This means that these regions are not only dark and silent, but also practically matter-free. If one could somehow float in the middle of such a void, the nearest galaxy might be hundreds of millions of light-years away in every direction, leaving one completely isolated in a sea of nothingness. It is fascinating to realize that despite their emptiness, voids are not entirely dead. Some of them contain faint wisps of gas, scattered dark matter, and a few small galaxies known as void galaxies. These lonely galaxies are special because they live in extreme isolation, far from the crowded environments of clusters. They tend to be small, irregular, and rich in gas, forming stars at a slower pace. Studying them helps astronomers understand how galaxies evolve without the influence of nearby neighbours. Comparing voids to galaxy clusters highlights just how uneven the universe is. A typical galaxy cluster, like the Coma cluster, can contain thousands of galaxies within a region of only a few million light-years. The gravitational forces inside a cluster are so strong that galaxies move at tremendous speeds, sometimes thousands of kilometers per second. Hot gas fills the space between galaxies, shining in X-rays, and dark matter forms an invisible halo that binds everything together. Now place that next to a void that stretches across hundreds of millions of light-years, where there are only a handful of galaxies and almost no hot gas at all. The contrast is staggering. It is like comparing a bustling city to a silent desert larger than the entire planet Earth. Yet both the cluster and the void are part of the same cosmic fabric, connected through the vast network of filaments that threads the universe. Superclusters, which are made up of many clusters linked together, show an intermediate level of density. They are the largest bound structures in the universe, containing countless galaxies and enormous amounts of mass. But even superclusters are surrounded by the dark, silent expanses of voids. The largest known superclusters, such as the Hercules Corona Borealis Great Wall, can extend for more than 10 billion light-years, an almost unimaginable scale. And still, beyond these cosmic walls lie vast stretches of emptiness that dwarf even those colossal formations. The cosmic web, with its filaments, clusters, and voids, is believed to have formed from small irregularities in the early universe. After the Big Bang, matter was spread almost evenly throughout space, but tiny differences in density caused gravity to pull matter together in some regions, while leaving others emptier. Over billions of years, matter continued to flow into dense regions, forming galaxies and clusters, while the less dense regions expanded into the voids we see today. Computer simulations of the universe's evolution, such as those created by the Millennium Simulation and Illustrious projects, have shown how these vast voids come into being. In these models, matter starts off as a nearly uniform mist. Over time, gravity draws it together into thin sheets and filaments. The spaces between these structures gradually become emptier, turning into the enormous voids that dominate the universe. The simulations match observations very closely, suggesting that the cosmic web we see today is the natural result of billions of years of gravitational evolution. While most galaxies live in filaments and clusters, the edges of voids mark boundaries where cosmic expansion and gravity meet. As dark energy pushes the universe apart, the voids expand faster than the denser regions. Galaxies near the boundaries of these voids are effectively being pulled outward, away from the centers of emptiness and toward the crowded filaments. This behavior means that cosmic voids are not static. They are dynamic and constantly changing, slowly growing larger as the universe ages. Astronomers have even mapped out hundreds of known voids across the sky, each one with a unique shape and size. Some are roughly spherical, while others are stretched or irregular. Their boundaries often connect in complex ways, forming a kind of honeycomb pattern across the cosmos. The largest voids can reach sizes of hundreds of millions of light-years, while smaller ones measure only tens of millions. Each void represents a region where gravity has lost the battle against cosmic expansion, leaving behind a near-perfect vacuum. In more recent studies, scientists have begun to use these voids to measure some of the most mysterious properties of the universe. For example, by studying how light from distant galaxies bends and shifts as it passes through or around voids, astronomers can estimate the influence of dark energy. The way light travels through these empty regions also helps test general relativity on cosmic scales. If gravity behaves differently across voids than it does near clusters, it could reveal new physics beyond our current understanding. The idea that the universe is mostly empty is one of the most profound and humbling discoveries in modern science. On human scales, even a single light-year sounds immense, but compared to a cosmic void, our entire galaxy becomes a mere speck. If someone could take a spaceship and travel across the Boötes Void at the speed of light, it would take more than 300 million years to reach the other side. That means the traveller would have to journey for a period longer than the time it took for dinosaurs to appear, evolve, and disappear on Earth, just to cross one void. And the Boötes Void is not even the only one. Other enormous voids have been identified, such as the Eridanus supervoid, which is associated with a mysterious cold spot in the cosmic microwave background radiation. The Eridanus supervoid stretches for nearly 1 billion light-years, making it one of the largest known structures of emptiness. Astronomers think it may play a role in the slightly cooler region of the cosmic background. as light travelling through such a vast void loses energy due to the expansion of space. The existence of these huge voids also affects how galaxies are distributed across the sky. When we look at large surveys of galaxies, we see that they form a pattern that looks like a foam of bubbles. The galaxies lie along the edges of the bubbles, forming walls and filaments, while the interiors of the bubbles are nearly empty. The overall effect is breathtaking, a vast interconnected web stretching across the entire observable universe. To compare scales more vividly, imagine that our galaxy, the Milky Way, is reduced to the size of a grain of sand. Then, the local group, which includes Andromeda and a few dozen smaller galaxies, would be the size of a small pebble. The Virgo cluster, which contains thousands of galaxies, would be the size of a large beach ball. The Laniakea supercluster with its 100,000 galaxies would be as large as a mountain. Yet a single void like Boötes would be so enormous that it could swallow thousands of such mountains and still appear nearly empty. This incredible scale of emptiness reminds us that most of the universe is not made of stars or galaxies at all. The visible matter that forms everything we can see makes up less than 5% of the total content of the cosmos. The rest is dark matter and dark energy, invisible and mysterious forces that shape the large-scale structure of everything. Voids are where dark energy dominates the most, driving the expansion of space at an accelerated pace. In the immense balance between the forces of gravity and expansion, the cosmic voids show us the universe's grandest contrast. Gravity gathers matter into galaxies, clusters, and superclusters, while dark energy pushes everything apart, carving out the vast empty spaces between them. The result is a cosmic landscape of extraordinary beauty and complexity, a universe that is both full and empty, crowded and lonely at the same time. Redshift surveys have become one of the most important tools in modern astronomy. They allow scientists to measure the distances to galaxies scattered across the vast universe, helping them map the large-scale structure of everything that exists beyond our own Milky Way. By carefully measuring how the light from these galaxies is stretched as it travels through expanding space, astronomers can learn not only how far away those galaxies are, but also how the universe itself has changed and grown over billions of years. One of the most fascinating uses of these measurements is in the discovery and study of cosmic voids, huge, almost empty regions that stretch across unimaginable distances. To understand how these redshift surveys help locate voids, it is first necessary to grasp what redshift means and why it serves as such a powerful cosmic yardstick. When a galaxy emits light, that light travels through the fabric of the universe, which is constantly stretching due to cosmic expansion. As space itself stretches, so does the wavelength of light moving through it. The longer the wavelength becomes, the redder the light appears when it finally reaches us. This shift toward the red end of the light spectrum is what astronomers call redshift. The more the light has been stretched, the greater the redshift, and therefore, the farther away the galaxy must be. In this way, redshift acts like a universal ruler, allowing scientists to measure distances not by physically moving closer, but by observing how much the light's colour has changed. This idea may seem simple, but it rests on one of the most profound discoveries in all of science: that the universe is expanding. This was first noticed in the early 20th century when astronomer Edwin Hubble found that nearly every galaxy he observed was moving away from us, and the farther a galaxy was, the faster it seemed to be receding. This relationship between distance and speed is now known as Hubble's law, and it forms the foundation for how redshift is used to measure distances. Over time, astronomers refined these measurements with better instruments, more sensitive detectors, and faster computers, leading to massive surveys of the universe that map millions of galaxies in three-dimensional detail. Each redshift survey begins with a careful selection of targets. Astronomers use telescopes equipped with powerful spectrographs, devices that can spread the light of a galaxy into a rainbow-like spectrum. Within that spectrum are tiny fingerprints, known as spectral lines, that correspond to specific elements and compounds found in stars and gas clouds. By comparing where these lines appear in a laboratory setting with where they appear in the galaxy's spectrum, scientists can determine how much the light has been shifted toward red. The difference reveals the galaxy's velocity away from us, which through Hubble's law can be converted into an approximate distance. Once the distances of many galaxies are known, astronomers can create a three-dimensional map of where everything lies. These maps reveal a universe that is not evenly filled with galaxies, but one that is patterned with intricate structures. There are dense clusters where thousands of galaxies gather, long thread-like filaments that connect those clusters, and vast, almost empty regions between them, the cosmic voids. These voids can span tens or even hundreds of millions of light-years, making them some of the largest known features in the cosmos. Redshift surveys are the only way to uncover these enormous spaces, because they provide the depth information necessary to see not just where galaxies are in the sky, but how far away they are from us and from each other. In the earliest days of cosmic mapping, astronomers could only measure the positions of galaxies in 2 dimensions, right ascension and declination, similar to latitude and longitude on Earth. These early catalogues showed where galaxies appeared in the sky, but could not tell how far away they were. When redshift measurements were added, the picture suddenly gained depth. Instead of a flat sky, scientists could now see the universe as a 3-dimensional web of galaxies. This was like turning a map into a globe, transforming a 2-dimensional pattern into a living, expanding structure. The earliest major redshift surveys were small by today's standards, sometimes measuring only a few hundred galaxies. But each one expanded humanity's understanding of how galaxies were distributed. In the late 1970s, a major breakthrough came with the first large-scale redshift surveys conducted by Margaret Geller and John Huchra at the Harvard-Smithsonian Center for Astrophysics. Their work revealed a complex pattern of walls, filaments, and empty regions. One of the most striking discoveries from their maps was the Great Wall, a gigantic structure stretching hundreds of millions of light-years across, as well as the discovery of vast voids, including the famous Boötes Void, a region so empty that it startled astronomers. As technology advanced, redshift surveys became more ambitious. Digital detectors replaced photographic plates, and computers became capable of analysing enormous amounts of data. The 2-degree field galaxy redshift survey, which began in the late 1990s, measured over 200,000 galaxies across a large portion of the sky. Around the same time, the Sloan Digital Sky Survey, or SDSS, began its mission, using a dedicated telescope in New Mexico to map millions of galaxies and quasars in 3 dimensions. The Sloan survey was a turning point because it combined precise imaging with detailed redshift measurements, producing some of the most complete maps of the cosmos ever made. These maps not only reveal the cosmic web, but also allowed astronomers to identify the size, shape, and distribution of the great cosmic voids that lie between the bright threads of galaxies. Redshift surveys do not just reveal where galaxies are, they also show how matter is distributed on the grandest scales. By comparing the clustering of galaxies in different regions, astronomers can test theories about how the universe evolved from the nearly uniform gas after the Big Bang into the complex web we see today. The voids found in these surveys are particularly important for such studies because they act as cosmic laboratories where the effects of dark energy, dark matter, and gravity can be observed with fewer complications. In dense regions, gravity pulls galaxies together, but in voids, the expansion of the universe dominates, allowing astronomers to study cosmic acceleration more clearly. The process of measuring redshifts, however, is not as simple as it might sound. The light from distant galaxies is incredibly faint, and the farther away a galaxy is, the longer its light has travelled, becoming stretched and dimmed along the way. To detect and measure such faint light, astronomers use large telescopes with wide mirrors that can collect as much light as possible. Observations are often made during clear dark nights, far from city lights. Each galaxy spectrum must then be analysed to identify the specific spectral lines, which may be weak or blended with others due to dust, gas, or motion within the galaxy. Despite these challenges, redshift surveys have reached farther and farther into the cosmos. Modern instruments like the Dark Energy Spectroscopic Instrument DESI, which began observations in the 2020s, are designed to measure tens of millions of galaxies with unprecedented accuracy. By doing this, astronomers can create maps that extend across more than 10 billion light-years, tracing how galaxies, filaments, and voids evolved over time. The data from such surveys help refine our understanding of the universe's composition. How much of it is made of normal matter, and dark energy. The discovery of voids through redshift surveys has dramatically changed how scientists view the universe's structure. Before these surveys, it was often assumed that galaxies were spread more or less evenly across space, with occasional clusters here and there. But the detailed maps showed something very different. a universe made of a complex network where the vast majority of space is nearly empty. Voids make up most of the universe's volume, while galaxies, stars, and planets occupy only a thin framework surrounding these immense empty regions. Each void identified by a redshift survey has unique characteristics. Some are roughly spherical, while others are irregular in shape, interconnected like bubbles in a frothy sea. The Boötes Void, one of the most famous examples, was found to be nearly 700 million light-years across. Within its enormous volume, only a few dozen galaxies are known to exist, so few that for a long time, astronomers could hardly believe such emptiness was possible. This discovery was made possible only through careful redshift measurements that revealed the distances and positions of galaxies in 3 dimensions, showing a gaping space where few galaxies existed. Redshift surveys also help scientists study how voids affect the motion of galaxies around them. In regions where matter is dense, gravity pulls galaxies inward, creating clusters and filaments. But in and around voids, the opposite happens. Galaxies are slowly pushed away as the void expands faster than the denser regions. By measuring these subtle movements through redshift data, astronomers can learn how the universe's expansion behaves on different scales. Such studies are particularly valuable for understanding dark energy, the mysterious force driving the acceleration of the cosmic expansion. In addition to mapping the visible universe, redshift surveys provide clues about invisible matter as well. Dark matter, which cannot be seen directly, influences how galaxies are distributed. The patterns found in redshift surveys, how galaxies cluster and where voids appear, offer indirect evidence of where dark matter must be concentrated. In this sense, redshift surveys act like cosmic fingerprints, revealing the hidden structures that shape the universe. The same data also help test competing models of cosmology, allowing scientists to see which theories best match the observed large-scale patterns. Over the decades, astronomers have refined how they interpret redshift data. They must account for many factors, such as peculiar velocities, small motions of galaxies caused by local gravitational forces, which can slightly distort the measured redshift. These distortions, when studied carefully, actually contain useful information about how matter moves and clusters. By modelling these effects, scientists can separate the expansion of space itself from the local motions of galaxies, achieving more precise distance estimates. With the growing amount of data from redshift surveys, astronomers have also developed new computational techniques to analyse it. Advanced algorithms and machine learning systems can now process millions of spectra, identify voids automatically, and calculate their sizes and shapes. These methods have allowed researchers to build detailed catalogues of cosmic voids, each one measured with remarkable precision. Such catalogues are not only maps of emptiness, but also tools for testing the fundamental laws of physics on scales far beyond what can be achieved in laboratories. The scale of modern redshift surveys is staggering. For example, the Sloan Digital Sky Survey alone has mapped over 3 million galaxies, covering a portion of the universe billions of light-years across. The Dark Energy Spectroscopic Instrument aims to collect spectra for more than 30 million galaxies and quasars, creating the largest 3-dimensional map of the universe ever made. Each point on these maps represents a galaxy, and when viewed together, they reveal the universe as a vast cosmic web of filaments surrounded by immense voids. These maps help scientists visualize how galaxies are arranged and how cosmic structures have evolved over billions of years. When astronomers plot the results of redshift surveys, the image that emerges is not random. The galaxies form long chains, sheets, and clusters, while voids appear as enormous gaps between them. The result looks like a sponge or foam, with dense regions connected by filaments and huge empty bubbles in between. This pattern is strikingly similar to what computer simulations predict, when the laws of physics are applied to the early universe after the Big Bang. Thus, redshift surveys serve as a bridge between theory and observation, confirming that our understanding of cosmic evolution matches what we actually see. Even more fascinating is how redshift surveys allow scientists to peer back in time. Because light takes time to travel, observing distant galaxies means seeing them as they were billions of years ago. The farther away a galaxy is, the older the light we receive from it. By studying redshift data from near and far galaxies, astronomers can trace how the universe changed over time, how voids grew larger, how clusters formed, and how dark energy began to dominate the expansion. Each redshift measurement is therefore not just a distance but also a timestamp in cosmic history. The role of redshift surveys in locating voids also extends to understanding how galaxies within or near these voids differ from those in dense regions. Observations show that galaxies inside voids tend to be smaller, less bright, and have less star formation than those in crowded clusters. These differences reveal how the environment influences galactic evolution. Redshift surveys make it possible to study these contrasts on a massive scale, linking the life cycles of galaxies to the large-scale structure of the cosmos. As instruments grow more sensitive, redshift surveys are expanding their reach even further. Future projects such as the Euclid mission and the Nancy Grace Roman Space Telescope will use space-based observatories to collect redshift data with greater accuracy, free from the blurring effects of Earth's atmosphere. These missions will allow astronomers to chart galaxies across more than 2/3 of the observable universe, mapping not only where the voids are today, but also how they evolved through cosmic time. Such observations may uncover subtle effects of dark energy, and possibly even new physics beyond current theories. The creation of a redshift survey is a massive collaborative effort involving hundreds of scientists, engineers, and programmers. The process can take years, from planning and instrument design to observation and data analysis. Each observation night adds another small piece to the cosmic puzzle. The data are then processed, calibrated, and released to the scientific community, often becoming the foundation for countless studies. Many discoveries about cosmic voids, dark energy, and the large-scale structure of the universe have come from open access to redshift survey data, allowing scientists everywhere to explore the cosmos together. Interestingly, redshift surveys do more than help scientists locate voids. They also help confirm the overall geometry and fate of the universe. By measuring how redshift relates to distance, astronomers can test whether the universe is flat, open, or closed. Current evidence from large surveys and cosmic background studies suggests that the universe is very close to flat, meaning it will continue expanding indefinitely. The distribution of voids supports this conclusion, as their size and shape match what theoretical models predict for a flat, accelerating universe dominated by dark energy. The universe is an enormous and mysterious place, filled with wonders that go far beyond the reach of our imagination. When astronomers look out into the vastness of the cosmos, they see galaxies, clusters, and filaments stretching across unimaginable distances. But they also see something else. Vast regions that appear almost completely empty, places where galaxies are few or even absent. These enormous regions are known as cosmic voids, and while they might seem like nothingness, they are among the most fascinating and mysterious structures in the entire universe. Understanding these immense spaces requires looking into the physics that governs them, the invisible forces and cosmic dynamics that shape the empty regions between the great clusters of galaxies. The story of how these voids formed begins in the earliest moments of the universe itself. After the Big Bang, which occurred around 13.8 billion years ago, the universe was not perfectly smooth. It was filled with an almost uniform sea of hot gas and radiation, but tiny differences in density, minute fluctuations, were already present. These small variations were like tiny wrinkles in an otherwise flat sheet. Over time, gravity began to act on these wrinkles. Areas that were slightly denser began to pull in more matter, becoming even denser, while regions that were slightly less dense became emptier as matter flowed away from them. As billions of years passed, this process continued and grew more extreme. Dense regions eventually formed the galaxies, galaxy clusters, and massive filaments that now make up the large-scale structure of the universe. Meanwhile, the less dense regions became emptier and emptier, evolving into the cosmic voids we observe today. What began as faint ripples in the early universe grew into the grand web of matter and emptiness that defines the cosmos. The forces that shape these vast voids are primarily the same ones that shaped everything else: gravity and dark energy. Gravity is the attractive force that pulls matter together. It is responsible for the formation of stars, galaxies, and clusters. But when gravity gathers matter in one place, it leaves behind regions with less matter elsewhere. These less dense regions begin to expand faster than their surroundings, creating voids. In this way, gravity doesn't just build, it also empties. As galaxies form and clump together under the pull of gravity, they pull material out of nearby regions. Think of it as a kind of cosmic migration. matter flows like a slow river from emptier areas into denser ones, drawn by gravitational attraction. Over cosmic timescales, these flows carve out enormous empty spaces, leaving behind vast cavities that can span hundreds of millions of light-years. However, gravity is not the only player in this grand drama. The other great force at work is dark energy, an invisible and mysterious form of energy that appears to be pushing the universe apart. Discovered in the late 20th century, dark energy accelerates the expansion of the universe. It acts in opposition to gravity, which tries to pull things together. In the cosmic voids, where matter is already scarce, the influence of dark energy is even stronger. With little matter around to resist it, the expansion in these regions happens faster than in denser areas. This makes voids grow even larger with time. As a result, cosmic voids are not static or frozen in space. They are dynamic structures, expanding, evolving, and interacting with their surroundings. The boundaries of a void, known as the walls or edges, are made up of filaments of galaxies and dark matter. These filaments form the skeleton of the universe, while the voids are the empty spaces between the bones. The interplay between these two regions, the dense filaments and the vast voids, creates a cosmic dance that has been going on for billions of years. The physics of this dance can be described using the equations of general relativity, which is Albert Einstein's great theory of gravity. General relativity tells us that matter and energy curve space itself, and this curvature affects how objects move. In dense regions, where there's a lot of matter, space is more curved, and gravity is stronger. In voids, where there is little matter, space is flatter and expands more freely. This uneven expansion is one of the key features that makes voids grow over time. When astronomers simulate the growth of the universe on powerful computers, they can actually watch this process unfold. They start with the tiny irregularities seen in the cosmic microwave background, the faint radiation left over from the Big Bang, and then let gravity and expansion do their work. Over billions of simulated years, matter clumps together into filaments and clusters, while vast empty regions appear between them. The resulting patterns closely match what astronomers see in real observations, confirming that voids are a natural outcome of cosmic evolution. Inside a cosmic void, the environment is extremely different from what we experience in our part of the universe. The density of galaxies can be less than 1/10 or even 1/100th of the average cosmic density. In some of the largest voids, there may be only a few lonely galaxies scattered across hundreds of millions of light years. These galaxies are like isolated islands in a dark cosmic ocean, far from the bustling galactic cities found in denser regions. The galaxies that do exist inside voids are also quite unusual. Because they form in regions with little gravitational competition, they often evolve differently from galaxies in clusters. Many void galaxies are smaller, have fewer stars, and are richer in gas. Some of them continue to form new stars long after similar galaxies in denser regions have stopped. In a sense, the emptiness around them gives them a kind of cosmic freedom. Without nearby neighbours to disturb them, they can quietly evolve at their own pace. But even though voids seem empty, they are not truly nothing. They contain dark matter, sparse gas, and faint cosmic radiation. Dark matter, though invisible, still exists in these regions, but at a much lower density than in the cosmic filaments. The behaviour of dark matter inside voids is particularly interesting to scientists, because it can reveal how gravity behaves in very low-density environments. Some alternative theories of gravity predict different behaviours in such regions, so studying voids can test fundamental ideas about the laws of physics. One of the fascinating aspects of cosmic voids is how they affect light that passes through them. Light from distant galaxies and quasars travels across billions of light years before reaching us. As it moves through the universe, it can be affected by the matter it encounters. In dense regions, gravity bends light, creating effects known as gravitational lensing. In voids, where matter is scarce, light can experience the opposite effect. It can be slightly accelerated or stretched. This creates a subtle signal known as the integrated Sachs-Wolf effect, which helps astronomers measure how dark energy influences the universe's expansion. By observing how light behaves as it passes through or around voids, astronomers can gain insight into both the geometry of the universe and the nature of dark energy itself. These measurements are incredibly delicate, requiring precise instruments and careful analysis. but they provide one of the few direct ways to probe the invisible forces shaping cosmic evolution. Another key aspect of void physics involves peculiar velocities, which are the motions of galaxies relative to the general expansion of the universe. In and around voids, galaxies experience what could be called a push from the expanding empty space. Inside the void, galaxies tend to move outward toward the walls, as if the emptiness is inflating beneath them. This outward motion makes the boundaries of voids more sharply defined, and can even cause nearby structures to drift apart faster than the cosmic average. These velocity patterns have been measured through redshift surveys, which record how much the light from galaxies is stretched by cosmic expansion. The redshift data reveal the three-dimensional structure of voids and their rate of growth. By comparing these observations with theoretical predictions, scientists can test whether the laws of gravity behave as expected on the larger scales. In recent years, astronomers have discovered that cosmic voids are also sensitive indicators of the universe's overall composition. Because they are so empty, their shapes and sizes respond strongly to the balance between matter, and dark energy. In a universe with more matter, voids would be smaller and less pronounced, because gravity would pull more material into dense structures. In a universe dominated by dark energy, voids expand more rapidly and become larger. The actual universe, as we observe it, seems to sit between these extremes, with about 70% dark energy, 25% dark matter, and only 5% ordinary matter. This mixture gives rise to the cosmic web we see today, with vast voids occupying most of the universe's volume. When you imagine the cosmic web, it helps to picture an immense three-dimensional network stretching across billions of light years. The bright threads of this network are made of galaxies, gas, and dark matter, while the vast spaces between them are the voids. Although the voids occupy most of the universe's space, they contain very little of its mass. Most of the matter is concentrated in the thin filaments and dense clusters that form the web's skeleton. The balance between these dense and empty regions is one of the most striking features of cosmic structure. The edges of voids are often sites of dynamic interaction. As matter flows out of the voids and into the surrounding filaments, it creates complex velocity fields and density contrasts. These flows can generate shock waves in intergalactic gas and influence the formation of new galaxies at the void boundaries. Observations and simulations suggest that the shapes of voids can change over time, sometimes merging with neighbouring voids to form even larger cavities. This process is known as void merging, and it resembles how bubbles combine in a foam. This analogy, though simple, captures an essential truth about cosmic evolution. The large-scale structure of the universe behaves somewhat like a frothing liquid, where gravity and expansion together sculpt patterns of clustering and emptiness. In this sense, the cosmic voids are like the bubbles in that universal foam, ever expanding and reshaping themselves as the universe grows older. Some of the largest known voids, such as the Boötes Void, are truly staggering in scale. The Boötes Void, discovered in the early 1980s, is about 300 million light-years across, and contains only a few dozen galaxies. Its discovery was one of the moments that forced astronomers to rethink how matter is distributed across the cosmos. Before then, many scientists imagined the universe as relatively uniform, with galaxies spread evenly throughout space. The recognition that such vast empty regions exist changed that view completely. It revealed that the universe is not homogeneous on smaller scales, but rather an intricate network of dense and empty regions, shaped by the combined action of gravity, dark energy, and cosmic expansion. The physics behind these empty regions is deeply connected to the early conditions of the universe. Those tiny density fluctuations that seeded the formation of voids were likely generated during a period known as cosmic inflation, an extremely rapid expansion that occurred just fractions of a second after the Big Bang. During inflation, quantum fluctuations in the early universe were stretched to cosmic scales. Some regions ended up slightly denser, while others were slightly less dense. These initial differences provided the blueprint for everything that followed: the galaxies, the filaments, and the voids. Dark matter and cosmic voids are two of the most mysterious features of our universe, and together they reveal a hidden side of the cosmos that is invisible to human eyes, but deeply influential in shaping everything we see. When scientists look into the universe, they do not just see galaxies, stars, and glowing clouds of gas. They also see enormous empty regions that stretch across unimaginable distances. These empty regions are known as voids, and they are not merely spaces without galaxies. They are windows into the invisible skeleton of the universe. Hidden beneath the darkness that fills these voids is something even more puzzling, something that cannot be seen or touched, yet exerts a powerful gravitational pull on everything: dark matter. Dark matter is one of the most important yet most mysterious substances ever proposed in science. It cannot be seen directly, it does not emit or absorb light, and no telescope can capture its glow. Yet scientists know it must exist because of the way it affects the things that can be seen. The stars within galaxies spin so fast that they should fly apart if only visible matter, like gas and dust, were holding them together. But they do not fly apart. Something unseen is providing the extra gravity needed to keep them bound. This invisible material, now known as dark matter, makes up most of the matter in the universe. Scientists estimate that about 85% of all matter is dark matter, while ordinary matter, the kind that makes up stars, planets, and people, accounts for only about 15%. When astronomers began mapping the universe on the larger scales, they found that galaxies were not scattered randomly across space. Instead, they were arranged in a vast and intricate web-like structure. Filaments of galaxies stretched for hundreds of millions of light-years, forming massive cosmic highways of matter. Between these filaments lay enormous empty bubbles, the voids. The discovery of this cosmic web changed how scientists viewed the universe. It showed that the cosmos was not just a collection of isolated galaxies floating in space, but a grand structure shaped by invisible forces. And the key to understanding why this structure exists lies in dark matter. Dark matter acts like the hidden framework upon which all galaxies and clusters of galaxies are built. In the early universe, tiny fluctuations in the density of matter began to grow under the influence of gravity. Where there was slightly more matter, gravity pulled in even more, leading to the formation of dense regions that would eventually become galaxies and clusters. Where there was slightly less matter, gravity was weaker, and those regions became voids, vast expanses with very few galaxies. The way dark matter clumped together determined where the galaxies would form and where the empty spaces would remain. In this sense, voids are the direct result of how dark matter distributed itself after the Big Bang. To understand this better, scientists often use computer simulations that recreate the early stages of the universe. These simulations start just after the Big Bang, around 13,800,000,000 years ago, when the universe was hot, dense, and almost uniform. Over time, as it expanded and cooled, dark matter began to gather into halos, dense knots of invisible mass. Ordinary matter, which interacts with light, followed the gravitational pull of these halos, collecting within them and eventually forming galaxies and stars. As dark matter continued to cluster, the spaces between these halos became emptier and emptier, forming the giant cosmic voids we observe today. When scientists simulate this cosmic process, the patterns they see in their virtual universes closely resemble what is observed in reality. Galaxies line up along filaments, forming walls and clusters, while between them lie enormous empty regions tens to hundreds of millions of light-years across. These simulations only make sense when dark matter is included. If they remove dark matter from the equations, the structures fail to form correctly. The galaxies would be distributed too evenly, and the voids would not appear as deep or as large. This shows that dark matter is not just an idea, it is an essential part of how the universe works. Voids provide scientists with a unique environment to study dark matter indirectly. Because voids contain so few galaxies and so little visible matter, the gravitational effects of dark matter stand out more clearly. In dense regions like galaxy clusters, the gravity from ordinary matter mixes with that of dark matter, making it harder to separate their effects. But in the near-empty regions of voids, the influence of dark matter can be isolated and measured more precisely. Scientists can study how galaxies on the edges of voids move, how light bends as it passes through these empty regions, and how cosmic expansion behaves inside them. All of these clues help reveal the hidden fingerprints of dark matter. One of the most powerful tools for studying dark matter through voids is a phenomenon called gravitational lensing. According to Einstein's theory of general relativity, gravity can bend light. When light from a distant galaxy passes through an area with a lot of mass, like a cluster of galaxies filled with dark matter, the light's path curves slightly, causing the distant galaxy to appear distorted or magnified. In cosmic voids, the effect is reversed. Because these regions have less matter than average, they bend light in the opposite way, creating a kind of anti-lens effect. By measuring how light from distant galaxies is distorted as it travels through voids, astronomers can estimate how much dark matter is missing from those regions compared to the cosmic average. Over the past few decades, large surveys of the universe have provided astronomers with maps containing millions of galaxies. By studying the distribution of these galaxies, scientists can locate the positions and sizes of voids. One of the most well-known examples is the Sloan Digital Sky Survey, which has mapped more than 1 million galaxies across vast stretches of space. From this data, astronomers have discovered that voids can range from about 30 million to more than 300 million light-years across. By analysing how light behaves across these voids, scientists can test predictions about dark matter and dark energy, the mysterious force that drives the acceleration of the universe's expansion. Voids do not just represent emptiness, they represent balance. Where there is less matter, the expansion of the universe proceeds more quickly. Inside a void, galaxies move away from one another faster than in denser regions, because there is less gravity to slow them down. In a way, voids act as cosmic laboratories that reveal how gravity behaves when matter is scarce. Because dark matter is what controls most of the gravity in the universe, studying the motion of galaxies around and within voids gives scientists a way to understand its distribution and properties. There is also another layer to this mystery: dark energy. While dark matter pulls things together through gravity, dark energy does the opposite. It pushes the universe apart. Scientists believe that dark energy makes up about 70% of the total energy content of the universe, while dark matter contributes about 25%, and ordinary matter makes up only about 5%. In cosmic voids, where there is little matter to resist expansion, the effects of dark energy become stronger. By measuring how quickly voids grow and expand over billions of years, scientists can learn how dark energy behaves and how it interacts with dark matter. One of the most fascinating discoveries about voids is how they can be used to test alternative theories of gravity. Some physicists believe that dark matter might not be a new form of matter at all, but rather a sign that our understanding of gravity is incomplete. In these alternative models, gravity behaves differently on large scales than it does within galaxies. Voids are perfect places to test such theories because they amplify the differences between normal gravity and modified versions. If gravity behaves even slightly differently in the near-empty spaces of voids, it could reveal whether dark matter truly exists as a physical substance or whether it is an illusion caused by the way we describe gravity. Observations of the cosmic microwave background, the faint glow left over from the Big Bang, also connect to the study of dark matter and voids. As this ancient light travels across the universe, it passes through regions of different densities. When it passes through a dense region filled with dark matter, the light gains a little energy. When it passes through a void, it loses some. This tiny effect, known as the integrated Sachs-Wolf effect, provides yet another way for scientists to measure how matter, including dark matter, is distributed across the cosmos. When researchers compare maps of voids with maps of the cosmic microwave background, they find correlations that match what dark matter models predict. Even though dark matter is invisible, scientists have several theories about what it might be made of. One idea suggests that it is composed of tiny particles that rarely interact with ordinary matter, known as WIMPs, short for weakly interacting massive particles. Another idea proposes that dark matter could be made of lighter particles called axions, which were first theorized as a solution to certain problems in particle physics. Some researchers even consider the possibility that dark matter might consist of primordial black holes formed soon after the Big Bang. Each of these possibilities would leave different imprints on the way dark matter clusters and the way voids evolve. By studying the size, shape, and growth of voids, scientists hope to narrow down which of these theories is correct. The shapes of voids themselves provide hints about how dark matter behaves. In some regions of the universe, voids are nearly spherical, while in others they are elongated or irregular. The arrangement and alignment of these voids depend on how dark matter interacts with itself and with normal matter. If dark matter particles can collide or scatter, even weakly, it could change the internal structure of voids over billions of years. On the other hand, if dark matter interacts only through gravity, The voids would maintain certain predictable shapes and density profiles. By comparing these patterns with computer simulations, astronomers can test which version of dark matter fits best with observations. Voids also reveal something important about how galaxies evolve. Galaxies that exist inside or near voids often look different from those found in denser regions. They tend to be bluer, smaller, and less massive, meaning they have fewer stars and less dust. This happens because galaxies in voids are isolated and receive fewer cosmic materials from surrounding regions. The lack of dark matter density in these areas slows down galaxy formation. In a sense, void galaxies live quieter, slower lives compared to their bustling counterparts in crowded clusters. Their isolation makes them excellent laboratories for studying how galaxies grow in environments with minimal gravitational influence from dark matter clumps. In recent years, astronomers have discovered some of the largest voids ever found, such as the Boötes Void, which lies in the constellation Boötes. It is about 330 million light-years across and contains only a few dozen galaxies within a volume that could normally hold thousands. The Boötes Void stands as a remarkable example of how dark matter sculpts the universe. Its emptiness tells scientists that dark matter did not cluster in that region after the Big Bang, leaving behind a bubble-like gap in the cosmic web. When scientists simulate how dark matter behaves on these scales, voids like Boötes naturally appear, showing once again that dark matter governs the architecture of the cosmos. Some astronomers describe the universe as a cosmic sponge, with filaments of dark matter and galaxies forming the solid framework, and the voids representing the empty bubbles between them. This comparison helps to visualize how dark matter shapes space on gigantic scales. Even though the voids appear empty, they still contain a faint mist of dark matter, just much less than the average density elsewhere. Measuring this faint dark matter density within voids is challenging but not impossible. Astronomers use gravitational lensing, galaxy motion, and cosmic background studies to estimate how much dark matter lingers within these immense cosmic hollows. Another interesting discovery involves how voids grow over time. In the early universe, matter was distributed more evenly, and voids were smaller. As billions of years passed, gravity pulled matter into denser regions, and the empty regions became even emptier. Voids expanded and merged with neighboring voids, creating even larger bubbles. This growth continues today as the universe expands. Dark matter plays a key role in this process by defining where matter collects and where it empties out. Without dark matter's invisible framework, the universe would not have such clearly defined filaments and voids. Astronomers have also noticed that voids can interact with one another, slowly merging to form larger structures. When two voids meet, the thin wall of matter that separates them collapses, and they combine into a single, larger void. This merging process mirrors how dark matter halos merge to form larger galaxies and clusters. Over cosmic time, this dance of merging voids and collapsing filaments gives the universe its dynamic, ever-changing structure. Every large-scale movement of galaxies and every empty stretch of intergalactic space is tied to the invisible pull of dark matter. While dark matter dominates the formation of structure, voids remind us of how important the absence of matter can be. In the same way that silence can define music, emptiness defines the shape of the cosmos. Without voids, galaxies would not be arranged in such striking patterns. The dark matter that forms the backbone of the universe also creates the conditions that allow voids to exist. These empty spaces are not mistakes or random gaps. They are fundamental to how the cosmic web holds together. New telescopes and space missions are opening even more opportunities to study the connection between dark matter and voids. Projects like the Euclid Space Telescope, launched by the European Space Agency, aim to map the geometry of the universe with unprecedented precision. Euclid's goal is to measure how galaxies are distributed and how cosmic voids evolve over billions of years, revealing more about both dark matter and dark energy. The Virasi-Rubin Observatory, with its massive survey camera, will soon create an even deeper map of the sky, capturing faint galaxies that trace the edges of voids. By combining these observations with theoretical models, astronomers hope to build a clearer picture of the hidden universe. Even though dark matter cannot be seen, its story is written in the structure of the cosmos. The distribution of galaxies, the shape of the voids, and the bending of light across the sky all bear witness to its invisible hand. When scientists study voids, they are not just studying emptiness, they are reading the cosmic script written by dark matter itself. The dance between matter and emptiness, between dark and visible, gives rise to the intricate web that fills the universe. Every galaxy, every cluster, every void tells a part of that story, showing how something unseen can sculpt everything that exists. The mystery of dark matter remains unsolved, but its connection to cosmic voids has provided scientists with one of the most powerful natural laboratories in existence. By studying these immense, nearly empty regions, they can test theories about gravity, measure the universe's rate of expansion, and probe the unseen forces that shape reality. The more astronomers learn about voids, the more they uncover the true nature of the universe's invisible matter, and as they continue to map the vast dark spaces between galaxies, they edge ever closer to revealing the secrets that dark matter has hidden since the dawn of time. Dark energy's influence on the universe is one of the greatest mysteries ever faced by modern science. It is something invisible, untouchable, and yet unbelievably powerful. It is the hidden force that seems to be pushing everything in the universe apart, driving galaxies away from one another at ever-increasing speeds. The discovery of this strange phenomenon changed the entire understanding of the cosmos, forcing scientists to accept that what we see with our eyes and telescopes represents only a small fraction of what is truly out there. To understand dark energy, astronomers and cosmologists have turned their attention to some of the most mysterious regions of all: cosmic voids, the vast empty spaces that stretch between clusters of galaxies. These enormous dark regions may appear to be nothing at all, but in reality, they hold valuable clues about the forces that control the shape, motion, and destiny of the universe itself. Cosmic voids are regions of space that contain very few galaxies, sometimes almost none. They are the opposite of galaxy clusters and filaments, which form the bright web-like skeleton of the cosmos. If one could look at the universe from far above, it would look like a gigantic sponge or a web of bright threads, with galaxies and clusters forming the dense knots and filaments, while the voids are the deep, empty bubbles that fill most of the volume in between. These voids are not small. Some stretch across hundreds of millions of light-years. The famous Boötes Void, for example, is so large that if the Milky Way galaxy were placed inside it, it could fit more than 1,000 times over and still not reach the edges. Voids like these make up most of the observable universe's volume, and even though they contain almost nothing, their emptiness tells a story about dark energy's influence and the strange way the universe is expanding. To understand how voids help reveal the effects of dark energy, it is necessary to look at how scientists discovered that the universe is expanding faster and faster. In the early 20th century, astronomer Edwin Hubble observed that distant galaxies were moving away from us and from one another, meaning that space itself was stretching. This discovery led to the idea of the Big Bang, the great explosion that started it all about 13,800 billion years ago. For a long time, scientists thought that gravity, the attractive force between all matter, would eventually slow down the expansion. But in the late 1990s, a team of astronomers studying distant supernovae noticed something completely unexpected. The expansion of the universe was not slowing down at all, it was speeding up. This shocking observation led to the concept of dark energy, a mysterious form of energy that seems to fill all of space and push everything apart. No one knows exactly what it is, but according to measurements, dark energy makes up about 70% of the entire energy content of the universe. Matter, both normal matter and dark matter, accounts for the remaining 30%. Because dark energy is spread evenly throughout space, it becomes more dominant in regions where there is very little matter, and that is where cosmic voids become extremely important. In the densest regions of the universe, like galaxy clusters, gravity is strong and resists the expansion caused by dark energy. But in the vast, nearly empty regions of cosmic voids, gravity is weak, and dark energy's influence can operate freely. This makes voids like giant laboratories for studying the effect of dark energy in its purest form. By observing how these voids grow, expand, and change over time, scientists can learn about how dark energy behaves and how fast it is pushing the universe apart. Voids are not completely empty. They contain a few lonely galaxies, clouds of gas, and traces of dark matter. But compared to the crowded regions of the cosmic web, their density is extremely low. When the universe first formed, matter was distributed more evenly, with small fluctuations in density. Over billions of years, gravity pulled matter together to form galaxies and clusters, leaving behind large regions that became emptier and emptier. As dark energy accelerated the expansion of the universe, these under-dense regions stretched even faster, making them even emptier. In a way, voids act like magnifying lenses that make dark energy's effects easier to detect, because the less matter there is, the more noticeable the acceleration becomes. When scientists map the universe using large surveys such as the Sloan Digital Sky Survey, they can measure the positions and redshifts of millions of galaxies. Redshift is a way of measuring how much the light from a galaxy has been stretched as it travels through expanding space. The greater the redshift, the farther away the galaxy is, and the faster it is moving away. By studying the pattern of redshifts, scientists can identify where the galaxies are concentrated and where the vast empty regions lie. These maps reveal an intricate web of filaments and voids stretching across the cosmos, with voids making up about 80% of the volume of the universe. Within these voids, galaxies tend to move in special ways that are affected by dark energy. Because the density is low, the gravitational pull from surrounding matter is weaker, allowing galaxies inside voids to drift outward faster than those in dense regions. Scientists measure this motion using what is called the void expansion rate. The faster galaxies inside a void move away from the void's center, the stronger the effect of dark energy appears to be. By comparing these motions across different voids and at different distances, astronomers can estimate how dark energy's strength may have changed over time. In addition to studying how galaxies move, researchers also analyze the shapes of voids. If the expansion of the universe were the same in every direction, voids would look roughly spherical. However, if dark energy affects space differently in different directions, or if gravity behaves differently at large scales, the voids might appear stretched or squashed when viewed from Earth. Scientists use a method known as the Alcock-Paczynski test to compare the apparent shapes of voids to their expected shapes. If a void appears distorted, it could mean that the expansion rate of the universe or the geometry of space itself is influenced by dark energy in ways not yet fully understood. One reason voids are such powerful tools in cosmology is that they are relatively simple. Galaxy clusters are extremely complex, with intense gravitational forces, hot gas, magnetic fields, and interactions between galaxies. Voids, on the other hand, are quiet and peaceful places by cosmic standards. Their simplicity makes it easier to isolate the effects of dark energy without too many other factors interfering. Some scientists have even described voids as clean experiments of the universe, places where the natural forces shaping cosmic evolution can be studied in their purest form. Dark energy's effect within voids can also be studied through a phenomenon called the integrated Sachs-Wolf effect. This occurs when light from the cosmic microwave background, the faint glow left over from the Big Bang, passes through a large void. As the light enters the void, it experiences a change in energy because of the weaker gravitational pull inside. If the universe were not accelerating, the light would gain back this energy when it exited the void, but because dark energy is stretching space, the light does not recover all its lost energy, leading to a slight change in temperature that can be measured. These tiny temperature differences, though extremely small, provide valuable evidence for dark energy's influence on large-scale cosmic structures. Computer simulations also play an important role in connecting voids and dark energy. Using powerful supercomputers, scientists can model how matter and energy evolved from the early universe to the present day. By changing the amount and nature of dark energy in their models, they can see how different universes would look and how voids would grow in each case. When they compare these simulations to real observations, they can narrow down which kinds of dark energy models fit best with what we actually see. Some of these models treat dark energy as a constant property of space itself, known as the cosmological constant. Others suggest that dark energy could change over time, behaving more like a dynamic field. Observations of voids are helping scientists decide which idea comes closer to the truth. In a way, voids are like time machines. Because light takes billions of years to travel from distant parts of the universe to Earth, looking at faraway voids allows astronomers to see them as they were long ago. By comparing young voids at great distances with older, nearby ones, scientists can trace how their shapes and sizes have changed over cosmic history. This helps them understand how the influence of dark energy has grown stronger over time. Observations show that voids in the early universe were smaller and less empty, while today they are larger and emptier, which fits perfectly with the idea that dark energy is driving an accelerated expansion. One of the most fascinating aspects of cosmic voids is their relationship with the surrounding cosmic web. The universe's structure resembles a vast three-dimensional network made up of filaments, clusters, and voids. The denser filaments form the skeleton of the cosmos, while the voids are like the enormous bubbles trapped between them. As dark energy pushes space apart, it stretches this web, making the filaments thinner and the voids wider. Over time, the contrast between the dense regions and the empty ones becomes more extreme, and this process helps scientists measure how strong dark energy's effect has been across different epochs. There are also special kinds of galaxies known as void galaxies, those that live inside the emptiest parts of the cosmos. These galaxies are isolated, far away from the influence of massive clusters, and they evolve differently because of their lonely environments. Studying these galaxies offers further insights into how dark energy shapes cosmic expansion. Their unusual properties, such as their slow rates of star formation and their smoother, less disturbed structures, show how the environment within a void is shaped by the large-scale expansion of space. Because dark energy acts more strongly where matter is sparse, the centers of large voids are places where its effects can be detected more clearly. In these regions, galaxies tend to move outward at slightly higher speeds than would be expected if only gravity were acting. Scientists measure these small differences using precision instruments and large surveys. The data gathered helps refine the value of the Hubble constant, which describes the rate of expansion of the universe. However, this measurement is not simple. Different techniques sometimes give slightly different results, leading to what is known as the Hubble tension. Voids may help resolve this mystery by offering independent ways to measure expansion that are less affected by gravitational complexities. Another way voids help scientists understand dark energy is by testing alternative theories of gravity. Some physicists believe that what we call dark energy might not be a new kind of energy at all, but rather a sign that our understanding of gravity is incomplete. These modified gravity theories predict different behaviors of cosmic structures at large scales, especially in low-density regions like voids. By studying how galaxies move inside voids and how light bends around them, researchers can compare these observations to the predictions of both standard and modified gravity models. So far, most results support the existence of dark energy as a real force, but the door remains open for new interpretations. Voids are also used to study something called baryon acoustic oscillations, faint ripples left over from sound waves that travelled through the hot plasma of the early universe before the first atoms formed. These ripples left an imprint in the distribution of galaxies and voids that can still be measured today. By studying the size and spacing of voids, scientists can measure how these ancient ripples have stretched over billions of years. Because dark energy affects how fast space expands, it also influences how large these ripples appear today. This makes voids a natural tool for measuring the cosmic expansion rate over time. Recent missions and surveys, such as the Dark Energy Survey, the Euclid Space Telescope, and the Vera Rubin Observatory, are mapping the universe in incredible detail, identifying thousands of new voids across vast cosmic distances. Each new void adds more information about how dark energy works and how it affects the growth of structure in the universe. With every new observation, astronomers refine their models, trying to piece together the story of how the universe evolved from a dense, hot beginning to the vast and mostly empty space we see today. The study of cosmic voids also helps scientists understand how the universe will continue to evolve. If dark energy remains constant or becomes even stronger, the expansion will keep accelerating, and the voids will continue to grow larger and emptier. Galaxies will drift farther apart until the night sky becomes increasingly dark, with fewer visible galaxies as time goes on. In this distant future, voids may dominate almost everything, leaving only isolated islands of matter surrounded by immense nothingness. Even though voids are enormous, they are extremely difficult to study. Their emptiness means there are few galaxies inside them to measure, and their boundaries are not sharply defined. Scientists must rely on careful statistical methods and computer simulations to identify and analyze them. But despite these challenges, the information they provide is uniquely valuable because it allows cosmologists to look at the effects of dark energy without interference from the chaotic forces found in dense regions. In recent years, new techniques such as gravitational lensing have allowed scientists to map the distribution of matter even invisible dark matter around and inside voids. Gravitational lensing occurs when light from distant galaxies is slightly bent by the gravitational pull of matter it passes by. By measuring these small distortions, astronomers can detect how much matter, both visible and invisible, lies in and around voids. This helps them see how dark energy interacts with dark matter and how both together shape the universe's structure. Another interesting aspect of studying voids is that they provide a kind of mirror image of galaxy clusters. Clusters show how gravity gathers matter together, while voids show how dark energy pushes matter apart. By comparing both, scientists can see the balance between attraction and repulsion in the universe, the struggle between gravity trying to pull things together and dark energy pushing them apart. This balance determines not only how fast the universe expands, but also how galaxies form, how stars are born, and how cosmic structures evolve. Through careful observation, astronomers have also noticed that the edges of voids can be regions of interesting activity. Galaxies along the boundaries of voids tend to move toward denser areas, forming walls and filaments. These motions help trace the flow of matter through space and provide additional ways to measure the rate of cosmic expansion. As dark energy drives the stretching of space, the matter at the edges of voids gets pulled along, creating patterns that can be detected in galaxy surveys. Scientists also use voids to study time delays in light traveling from distant galaxies. Because space inside a void is expanding faster than average, light takes slightly longer to cross it than it would through denser regions. By measuring these subtle differences, researchers gain more information about how space itself is expanding under the influence of dark energy. Even though these effects are extremely small, advances in technology and data analysis are making it possible to detect them more accurately than ever before. The discovery of dark energy and the realization of its influence on voids have transformed cosmology into a new era of exploration. The universe is not just expanding, it is accelerating, and this acceleration is happening everywhere, from the smallest atom to the largest cluster of galaxies. Voids, by their very emptiness, make this acceleration visible. They serve as cosmic amplifiers that reveal what cannot be seen directly. Every measurement of a galaxy moving away from the center of a void, every distortion of light passing through a vast empty region, and every comparison of void shapes across billions of years brings scientists closer to understanding the invisible engine driving the universe apart. In the future, as instruments become more sensitive and surveys more complete, the role of voids in studying dark energy will continue to grow. By combining observations of voids with those of supernovae, galaxy clusters, and the cosmic microwave background, scientists can build a more complete picture of how the universe behaves on every scale. The hope is that one day, these vast empty spaces will reveal the true nature of the force that is shaping everything, the mysterious dark energy that fills the universe and determines its ultimate fate. Through these silent expanses of almost nothingness, the story of the universe's most powerful and elusive force continues to unfold. Even though voids may appear to be the quietest places in existence, they speak volumes about the deep and unstoppable expansion that defines the cosmos itself. When scientists look deep into the universe, they see countless galaxies forming an enormous web that stretches across the cosmos. This web is made up of long filaments filled with stars, gas, dust, and galaxies that connect like threads across unimaginable distances. Between these filaments, however, lie enormous dark regions, vast and almost empty spaces known as cosmic voids. These voids are like immense bubbles scattered throughout the universe, and though they appear empty at first glance, some of them contain lonely galaxies drifting in isolation. These rare galaxies are called void galaxies, and they are among the most fascinating and mysterious objects astronomers have ever studied. Understanding them helps scientists explore how galaxies form, how the universe has evolved, and how the hidden forces of dark matter and dark energy shape everything we see. A cosmic void can stretch across hundreds of millions of light years, a scale so immense that it is almost impossible to imagine. To put it into perspective, if our Milky Way galaxy were a grain of sand, a typical void could be the size of a continent. Within this enormous emptiness, there are only a few lonely islands of matter, galaxies that somehow managed to form in places where there is almost nothing. These galaxies are rare, fragile, and quite different from the ones that live in the crowded filaments of the cosmic web. They are the survivors of isolation, existing in regions where gravity is weak, where gas is scarce, and where interactions with other galaxies are almost non-existent. When astronomers first began mapping the universe in the late 20th century, they were astonished to discover that galaxies were not spread evenly across space. Instead, galaxies gathered into long chains, walls, and clusters, leaving behind large areas that seemed almost empty. These areas were the voids. Later, as technology improved and more detailed redshift surveys were conducted, scientists realized that even inside these huge empty spaces, some galaxies existed, though very few. These discoveries sparked a new curiosity. What kind of galaxies could survive in such isolation? How did they form in the first place? And what could they tell us about the universe's history? The first step toward understanding these mysterious galaxies was to observe them closely and compare them with those found in denser regions of space. Astronomers discovered that void galaxies tend to be smaller, bluer, and richer in gas compared to galaxies in crowded clusters. They often contain large amounts of hydrogen gas, the raw material for making new stars, and as a result they are frequently sites of ongoing star formation. This makes them appear youthful and active, even though they may be billions of years old. The lack of nearby galaxies means that these void dwellers have evolved differently, untouched by the gravitational tugs, collisions, and mergers that constantly shape galaxies in more crowded regions. In normal clusters or filaments, galaxies frequently interact. They collide, merge, or tear material from each other, forming new stars or triggering bursts of energy. Over billions of years, this process transforms galaxies. Small ones combine to form larger ones, spiral galaxies can turn into elliptical ones, and some lose their gas completely. But in the emptiness of a void, there is no such chaos. A void galaxy drifts alone, undisturbed for ages. Without frequent interactions, it can keep much of its original structure. This makes void galaxies a kind of time capsule, preserving the conditions of the early universe. By studying them, astronomers can learn what galaxies might have looked like before billions of years of collisions reshaped most of the universe. Because void galaxies are so isolated, they also provide a unique way to study how galaxies grow without the influence of external forces. In dense regions, it's hard to separate the effects of environment from the natural process of galaxy evolution. But in a void, there are no nearby neighbours to interfere. Every change a void galaxy experiences comes mainly from its own internal processes, like the collapse of gas clouds, the birth and death of stars, or the influence of dark matter within its own halo. This makes void galaxies extremely valuable for testing theoretical models of galaxy formation. Interestingly, the dark matter distribution in voids is also quite different from that in dense regions. While filaments and clusters are packed with dark matter, voids contain much less of it. Yet even there, dark matter is not completely absent. It forms a faint and invisible skeleton upon which the few existing galaxies are built. Scientists believe that void galaxies form in small dark matter halos that somehow manage to gather enough gas to ignite star formation. These galaxies may therefore represent the lowest density environments, where dark matter still managed to create visible structures. Studying them helps astronomers understand how dark matter behaves on the larger scales, and how it influences galaxy birth in the universe's most barren regions. Some of the most detailed studies of void galaxies come from modern astronomical surveys that map the universe in 3 dimensions. Instruments like the Sloan Digital Sky Survey and other redshift mapping projects have identified thousands of cosmic voids and the rare galaxies that live inside them. By comparing the properties of these galaxies to those found elsewhere, researchers have discovered patterns that reveal much about cosmic evolution. For example, void galaxies tend to rotate faster than similar galaxies of the same mass found in denser areas. They also appear to have thinner disks and fewer signs of disruption. This might be because they have lived undisturbed for billions of years, allowing their natural structure to remain intact. In addition, the chemical composition of void galaxies tells a fascinating story. Because they live in isolation, they often contain fewer heavy elements, what astronomers call metals. These elements are produced by generations of stars through nuclear fusion and supernova explosions. In crowded regions, galaxies constantly exchange gas and stars through collisions, spreading metals across space. But in voids, such interactions are rare. This means that void galaxies retain a more primitive composition, similar to the early galaxies that formed not long after the Big Bang. They are in a sense fossils of the early cosmos, showing what the universe's first galaxies might have looked like before they enriched themselves with heavier elements. Despite their isolation, void galaxies are not all the same. Some are small dwarf galaxies, barely large enough to hold a few million stars. Others are surprisingly large spirals, almost as big as the Milky Way, though such cases are rare. Their variety shows that even in emptiness, nature finds ways to create diversity. Some void galaxies are forming new stars at a steady rate, glowing with blue light from young stellar populations. Others seem quieter, with less gas and slower star formation. This range of behavior suggests that even in the most desolate regions of space, different paths of evolution are possible. One particularly interesting discovery is that some void galaxies appear to be connected by faint filaments of gas, forming miniature networks within the voids themselves. These small structures resemble a tiny version of the cosmic web, suggesting that even in emptiness the same fundamental patterns repeat on smaller scales. This fractal-like structure hints that the processes shaping the universe are universal. They work the same way everywhere, even in the loneliest corners of space. Studying void galaxies also helps researchers understand the role of cosmic environment in shaping galaxies. In denser areas, gravity from nearby galaxies and clusters can strip gas away, heat up the intergalactic medium, and shut down star formation. In voids, the opposite is true. Galaxies have access to their gas for much longer. This allows them to continue forming stars even when galaxies in denser regions have already stopped. Because of this, void galaxies often appear younger, bluer, and more active. They are like the late bloomers of the universe, still shining with youthful energy while their crowded cousins have long since aged. Void galaxies also serve as natural laboratories for studying how the universe's large-scale structure affects smaller cosmic systems. Their motions, shapes, and growth patterns reflect the gravitational influence of surrounding voids and filaments. By measuring how these galaxies move and spin, astronomers can infer how matter and dark energy are distributed on the larger scales. Since voids expand faster than the average universe due to their low density, the galaxies within them provide valuable clues about cosmic expansion and the mysterious acceleration driven by dark energy. One of the best-studied voids in our cosmic neighborhood is the so-called Boötes Void, discovered in the early 1980s. It is an enormous region of space nearly 330 million light-years across and almost completely empty. Yet, even inside this vast desert of nothingness, a few lonely galaxies have been detected. These rare inhabitants are examples of void galaxies that somehow formed and survived in an environment where almost no matter exists. Observing them gives scientists direct insight into how galaxies behave when cut off from the rest of the universe. Over the years, telescopes both on the ground and in space have gathered data from void galaxies across different parts of the sky. The Hubble Space Telescope, with its sharp vision, has captured images showing the delicate structures of these galaxies, their spiral arms, glowing star-forming regions, and faint halos. In some cases, these galaxies look surprisingly normal, like miniature versions of spirals found elsewhere. In others, they appear distorted or irregular, with uneven patches of stars and gas. This diversity shows that isolation does not always lead to simplicity. Even in solitude, galaxies can evolve in complex and unexpected ways. A key mystery surrounding void galaxies is how they obtain their gas in the first place. Since voids contain so little matter, where did the material for star formation come from? Some scientists suggest that during the early stages of the universe, when matter was still more evenly spread out, small fluctuations in density allowed certain regions within voids to collect just enough gas to form galaxies. Others propose that cosmic filaments extending through the voids funneled gas toward these small dark matter halos, slowly feeding them over billions of years. Either way, their existence shows how creative and resilient nature can be, able to form galaxies even in places where conditions seem least favorable. Another question scientists explore is how these galaxies evolve without frequent interactions. In denser regions, galaxy mergers are common and play a major role in growth. But in voids, such events are rare. Without mergers, galaxies grow more slowly, mainly by converting their internal gas into stars. This gradual process leads to smoother and more stable structures. Some computer simulations suggest that void galaxies could remain relatively unchanged for most of the universe's history, evolving peacefully while others experience violent transformations. This calm existence makes them excellent laboratories for testing models of internal galaxy evolution, free from the external disturbances that dominate elsewhere. Astronomers also use radio telescopes to study the hydrogen gas in void galaxies. Hydrogen emits a faint radio signal at a specific wavelength of 21 centimeters, allowing scientists to map how much gas is present and how it moves within the galaxy. Observations show that void galaxies often have extended hydrogen disks stretching far beyond their visible stars. This means they have large reserves of fuel for future star formation. It also suggests that void galaxies may continue to evolve long into the future, forming new stars even as galaxies in crowded environments exhaust their supplies. Some researchers think that studying void galaxies might also shed light on the mysterious problem of missing dwarf galaxies. According to theoretical models of dark matter, there should be many more small galaxies than we actually observe. These tiny galaxies are thought to be too faint or too diffuse to detect easily. However, in the quiet environment of a void, such galaxies might survive more easily, unperturbed by gravitational disturbances. Detecting them could help confirm or adjust our understanding of dark matter and its role in galaxy formation. Modern computer simulations of the universe have become powerful enough to recreate voids and the galaxies within them. By comparing simulated void galaxies with those observed in reality, scientists can test their theories about how matter clusters and evolves. These simulations show that even the emptiest regions of space contain a faint network of dark matter filaments, with small galaxies forming where these threads intersect. The results support the idea that void galaxies are the natural outcome of cosmic evolution. They are simply the rare survivors in the universe's vast underpopulated zones. Because voids expand faster than other regions, they are also sensitive probes of cosmological parameters. The rate at which void galaxies move apart can reveal the influence of dark energy, the mysterious force that accelerates cosmic expansion. By observing the redshifts of void galaxies, astronomers can measure how quickly these galaxies are receding and compare it to theoretical models. These studies help refine our understanding of the overall shape and fate of the universe. Voids, despite their emptiness, thus hold some of the most powerful clues about the universe's hidden forces. Void galaxies also offer a unique contrast to galaxies in clusters. In galaxy clusters, intense radiation, high temperatures and strong gravitational forces strip gas away from galaxies, quenching their ability to form new stars. In voids, where such effects are absent, galaxies can retain their cold gas for much longer. This difference makes it possible to study how the environment alone affects galaxy evolution. By comparing the two extremes, dense clusters and empty voids, scientists can isolate the fundamental processes that govern how galaxies change over time. As telescopes become more powerful, astronomers continue to discover new void galaxies that push the limits of observation. Some are so faint that they can barely be detected even with long exposures. Others are surprisingly bright, standing out as lonely beacons in the cosmic dark. Future observatories, such as the Vera C. Rubin Observatory and next-generation space telescopes, are expected to find many more of these isolated systems, mapping the universe's most desolate frontiers in greater detail than ever before. The study of void galaxies also connects deeply with human curiosity about isolation and survival. Just as life on Earth has adapted to extreme environments, deep oceans, frozen poles and scorching deserts, galaxies too find ways to exist in the cosmic wilderness. Their quiet endurance in a nearly empty universe captures the imagination. They remind us that even in the deepest silence of space, creation continues. Stars are born, light travels across billions of years, and the universe maintains its rhythm even where it seems most empty. On a larger scale, void galaxies may also help refine our understanding of cosmic reionization, the era when the first stars and galaxies lit up the universe after its dark ages. Because void galaxies are less influenced by external radiation fields, they might retain signs of the early intergalactic medium state. Their properties could offer indirect evidence about how the universe transitioned from opaque to transparent. In this way, studying galaxies in today's voids can teach us about events that happened more than 13 billion years ago. Even though void galaxies are few and far between, their importance in cosmology is immense. They help answer questions about how galaxies form, how dark matter and dark energy shape the universe, and how cosmic structures grow from small fluctuations to the vast web we see today. They also challenge our imagination, showing that life, light, and structure can emerge in even the most desolate cosmic environments. Every time astronomers discover a new void galaxy, they are reminded that the universe still holds countless secrets in its emptiest places. Looking across the billions of light-years of space, the sight of a single galaxy shining alone within an enormous void is both scientifically intriguing and deeply poetic. It speaks of persistence in the face of isolation, of order emerging out of near-nothingness. Each of these rare galaxies is a tiny spark within an endless cosmic sea, a messenger from the quiet side of creation. By studying them, scientists continue to uncover how the universe, in all its vast emptiness, remains alive with motion, energy, and light. Light and gravity are two of the most fascinating forces in the universe. Light reveals the hidden beauty of galaxies, stars, and nebulae, while gravity shapes everything we see in the cosmos, from the smallest dust clouds to the largest clusters of galaxies. But what happens when light and gravity pass through the emptiest parts of the universe? The vast cosmic voids where almost nothing exists. These enormous empty regions, sometimes stretching hundreds of millions of light-years across, may seem lifeless and insignificant, but in truth, they play a powerful and surprising role in the way light travels and in the way galaxies move. The study of how these voids influence light and gravity gives astronomers a completely new way to understand how the universe is built and how it continues to change. A cosmic void can be described as a region of space that contains far fewer galaxies, stars, and matter than the average parts of the universe. In these gigantic cosmic deserts, matter is incredibly thinly spread out. There might be a few lonely galaxies scattered across vast distances, separated by hundreds of millions of light-years of almost complete emptiness. Even though we call them empty, they still contain small amounts of gas, dark matter, and radiation, but these are extremely weak compared to what exists in more crowded regions like galaxy clusters. Yet, despite being empty, voids still interact with the forces that govern the universe, especially gravity and light. Gravity is one of the most mysterious and yet most essential forces in the cosmos. It is the invisible glue that keeps galaxies together and causes planets to orbit stars. Normally, we think of gravity as something that pulls objects toward areas with a lot of mass, like a planet pulling on a moon or a black hole pulling in nearby stars, but cosmic voids present the opposite situation. They are not filled with massive structures, they are defined by a lack of mass. This makes their gravitational behavior quite different. Instead of pulling things inward like galaxy clusters do, voids exert a kind of outward push on nearby matter. This happens because the surrounding regions of the universe, which contain more matter, have stronger gravitational pulls. As a result, the empty spaces of voids expand faster than the rest of the universe, and galaxies around their edges are slowly pulled outward, moving away from the centers of the voids. This strange gravitational effect of voids can even influence how galaxies evolve. A galaxy located near the edge of a void experiences weaker gravitational attraction compared to galaxies that are part of dense clusters. Over billions of years, this difference can change how gas flows into or out of galaxies, how stars form, and even how the galaxy spins. Astronomers have found that galaxies near the edges of voids often tend to be younger, bluer, and more active in star formation compared to galaxies in crowded environments, which are older and redder. This shows that even emptiness can shape the story of galaxies in a very real way. But gravity's effect inside a void doesn't end there. The most remarkable influence of gravity, and one that connects directly with light, is the way it bends the path of light travelling through space. According to Einstein's theory of general relativity, mass curves the space around it, and light follows this curved path. When light from a distant galaxy or quasar passes near a massive cluster, the cluster's gravity acts like a lens, bending and sometimes magnifying the light. This effect is called gravitational lensing, and it has been one of the most powerful tools for mapping invisible matter in the universe, especially dark matter. However, the same principle applies in reverse when light passes through a void. Because a void has less mass than average, it bends light in the opposite way. Instead of focusing light like a magnifying glass, a cosmic void causes light to spread slightly apart. This phenomenon is sometimes referred to as gravitational lensing by underdense regions, or more simply as anti-lensing. Light passing through a void is affected by the lack of gravitational pull. Its path becomes slightly straighter than it would be in a more massive region. As a result, The images of distant galaxies seen through voids may appear slightly dimmer, smaller, or stretched differently compared to those seen through normal or dense parts of the cosmos. The effect is extremely subtle, but with sensitive telescopes, astronomers can measure it. By studying how light is altered by both massive clusters and empty voids, scientists can create more complete maps of the cosmic web, the vast network of filaments, walls, and empty bubbles that form the structure of the universe. One of the key effects that voids have on light is known as the integrated Sachs-Wolf effect. This effect describes how light from the early universe, specifically the light that forms the cosmic microwave background, changes as it travels through regions of different density. When cosmic background photons pass through a dense region, like a galaxy cluster, they gain energy from the strong gravitational field, and when they climb out, they lose some of that energy. Normally, the two processes cancel out, leaving the photon's energy unchanged. But if the universe is expanding at an accelerated rate, as it is due to dark energy, then the gravitational potential wells and hills evolve as the light travels. In the case of a void, the gravitational potential becomes shallower over time. This means that as photons leave the void, they lose less energy than they gained when entering, which slightly increases their overall energy. This produces tiny, measurable changes in the temperature of the cosmic microwave background. These small changes help astronomers study the large-scale structure of the universe and confirm the influence of dark energy. This interaction between light, gravity, and cosmic voids tells us that even the emptiest parts of the cosmos have a role in shaping what we see. When light passes through a void, it doesn't just move in a straight line unaffected, it experiences changes in direction, brightness, and timing. The travel time of light across a void can be slightly different compared to travel through denser regions because the gravitational potential is lower. This subtle difference is another form of gravitational redshift or blue shift. Depending on the direction of travel, the result is that cosmic voids can slightly alter the apparent position and colour of distant objects in the sky. For example, if astronomers observe two galaxies at similar distances but in different directions, one through a void and one through a dense cluster, their apparent brightness and redshift might not match perfectly. The galaxy seen through the void might appear a bit dimmer, or its redshift might indicate it is slightly farther away than it really is. This happens because the light's journey through an underdense region makes it lose less energy, compared to light travelling through more massive areas. To correct these differences, astronomers must take into account the distribution of voids along the line of sight. Without this correction, measurements of cosmic distances and expansion rates could be slightly biased. Therefore, studying the effect of voids on light is not just an interesting curiosity, it is crucial for precision cosmology, especially when measuring how fast the universe is expanding. The bending of light around and through voids can also be used to detect their presence and map their shapes. Astronomers often use a technique called weak lensing tomography, which analyzes the slight distortions in the shapes of distant galaxies caused by gravitational lensing and anti-lensing. By stacking and comparing thousands or even millions of galaxy images, scientists can reconstruct the three-dimensional distribution of matter and emptiness across the universe. This allows them to detect voids that might otherwise be invisible, since many of them do not contain enough galaxies to be seen directly. Through these lensing maps, the cosmic web comes alive, showing the intricate dance between light and gravity across billions of light years. Voids do not just influence light passing through them, they also shape the motion of nearby galaxies. Since voids have weaker gravitational fields, galaxies located near them feel less gravitational attraction toward the void center. Instead, they are gently pushed outward by the stronger pull of the surrounding denser regions. This creates a characteristic flow pattern in the universe, where galaxies move away from the centers of voids. This movement can be observed as peculiar velocities, which are deviations from the overall cosmic expansion known as the Hubble flow. By carefully measuring these velocities, astronomers can estimate the size, depth, and density contrast of cosmic voids. In a sense, galaxies act as tracers, marking the invisible boundaries of these enormous bubbles. One particularly interesting example is the KBC void, named after the astronomers Keenan, Barger, and Cowie who described it. Our own Milky Way galaxy is located near the edge of this vast underdense region, which stretches for hundreds of millions of light years. Some scientists have suggested that the local void might influence certain cosmological measurements, such as the observed rate of the universe's expansion. Because light from distant galaxies passes through this underdense region before reaching us, it might appear slightly different, leading to minor but important effects on how we interpret redshifts and distances. This local void therefore provides an opportunity to study firsthand how emptiness affects light, gravity, and cosmic motion. The gravitational effects of voids also contribute to the large-scale dynamics of the universe. As voids expand faster than denser regions, they help stretch the cosmic web, amplifying the differences between empty and crowded areas. Over billions of years, matter continues to flow away from the centers of voids and collect in thin walls and filaments that form the boundaries between them. This process of cosmic evacuation makes voids larger and emptier over time, while galaxy clusters and filaments become denser. The gravitational field of a void, though weak, plays a critical role in shaping this ongoing evolution. By studying the movement of galaxies around voids, astronomers can gain insights into how gravity operates on the largest scales and how the universe's structure grows. Another subtle but important influence of voids on light and gravity involves time itself. In the framework of general relativity, gravity affects not just space but also time. In regions of high mass density, time runs slightly slower compared to emptier regions. This means that in the heart of a cosmic void, where gravity is weakest, time passes a bit faster relative to regions near massive clusters. Although the difference is tiny and impossible to notice in everyday experience, it can accumulate over billions of years and affect the timing of cosmic signals. For instance, when astronomers observe light echoes or gravitational waves passing through different regions, they must consider how voids might alter their timing. This connection between gravity, light, and time in voids adds yet another layer of complexity to our picture of the universe. There are also hints that cosmic voids may enhance our understanding of dark energy. Because voids expand faster than average, they are particularly sensitive to the effects of dark energy, the mysterious force driving the universe's accelerated expansion. By observing how galaxies move near voids and how light bends across them, scientists can measure the rate of expansion in these regions. Any deviation from the expected behavior could provide clues about whether dark energy behaves the same everywhere or changes depending on the environment. In this sense, voids act as cosmic laboratories for testing gravity and the fundamental laws of physics. To measure these delicate effects, astronomers rely on some of the most powerful telescopes and surveys ever created. Projects such as the Sloan Digital Sky Survey and the Dark Energy Survey have mapped millions of galaxies across vast portions of the sky. By identifying regions with lower than average galaxy density, they can pinpoint the locations of cosmic voids. Then, by analyzing how light from background galaxies is slightly distorted, they can estimate how gravity behaves in these empty regions. Future missions like the Euclid satellite and the Vera C. Rubin Observatory will produce even more detailed maps of voids and the lensing effects they create. These observations will help refine our understanding of how light interacts with gravity in the least populated parts of the cosmos. On smaller scales, researchers also use computer simulations to model how light and matter behave inside voids. These simulations start with conditions shortly after the Big Bang and follow the universe's evolution over more than 13 billion years. As the simulation runs, it shows how matter clumps together under gravity, forming filaments and clusters, while large empty regions emerge between them. When scientists simulate how light travels through this digital universe, they can reproduce the weak lensing and redshift effects seen in observations. By comparing real data with these models, astronomers can test theories of gravity, dark matter, and dark energy with increasing accuracy. Even though cosmic voids lack the dramatic features of supernovae or black holes, they are equally important in understanding how the cosmos works. Their influence on light and gravity may be subtle, but over cosmic distances, those small effects accumulate and become powerful tools for measurement. For example, when astronomers study the cosmic microwave background, the ancient light left over from the early universe, they find tiny variations in temperature and brightness. Some of these fluctuations are caused by photons traveling through vast cosmic voids, slightly gaining or losing energy as they move through different gravitational potentials. By studying these patterns, researchers can infer the distribution and size of voids billions of light years away, giving them a window into the universe's large-scale structure at its earlier stages. Another fascinating aspect of voids' influence on gravity is their potential to test alternative theories of gravity beyond Einstein's general relativity. Some modified gravity theories predict that gravitational forces behave differently in underdense regions compared to dense ones. Because voids provide such extreme low-density environments, they serve as ideal testing grounds for these theories. If gravity were to weaken or strengthen differently in voids than expected, the motion of galaxies and the bending of light would reveal those differences. So far, observations seem to support general relativity, but the precision of these measurements continues to improve, and cosmic voids remain one of the best ways to check the limits of our understanding of gravity.